go. All right, welcome everybody. Today is the 30th of November in Dallas, at least. And this is Dallas Personal Robotics Group Robot Builders Night Virtual. We're just going to do the usual and go around the table and share our recent successes or questions or whatever. Just a little bit of housekeeping. Last week, we had someone suggest a new membership level for folks that aren't likely or able to attend on a regular basis in person. So just to follow up on that, we have had some offline discussions among the DPRG board. And as I read the rules, we probably can't do anything about it until a club vote. But thankfully, one of those seems to be coming up soon anyhow. So let's see what happens with that. Then on the 11th of December in our monthly meeting, we have Paul talking about his experience self-driving truck world. 8th of January is our kind of annual meeting where, we're a formal 501c, so we'll have election and last year review and next year planning. And then we know for sure that Jack Jones is going to have a presentation at some point after that, but the date isn't picked yet. And we're always open for looking for people who want to jump in and sign up for something at some point along the way. Any other housekeeping before we dive in? Someone's got some echo, but it's not too bad. Okay. Well, then without further ado, I believe we'll go Pat first. And then depending on who's ready, either Carl or Iron Rain, and then Doug D, if we can, something like that. So Pat, floor is yours. What you got?
Okay, so last week, after getting my working on the wooden monster and getting my motor driver running, wheels spinning, I've been working on tuning some PID loops. So with the help of David Anderson, I managed to figure out what I was doing wrong with the GNU plot, got that working, and I've got a couple plots to bring up. That's all. So I'm going to present my screen. So there I've got, I think it's the left motor. And I don't know if you guys can see that. The blue is the output. The green line is the actual speed, and the red is the set point.
Pat, when you say output, the output of the PID controller?
The output of the PID controller, yes. What's going to my motor driver.
And the red is the input to the PID controller?
Red is my set point. And
the green is the actual measured from the wheels.
Yes.
Okay.
So red and green are in actual engineering units like centimeters per second, but I guess the blue is some other units, right?
The blue is an output of, I've scaled it to plus or minus 150 maximum. And it's just the output of my PID loop.
And you scale that so it would fit on the screen, on the graph?
Nope. Well, right now I've widened it. So the output.
That 60 blue, does that correspond to like a 60% PWM duty cycle, or does it just? I mean, what does it correspond to?
Well, the duty cycle that can go to the motor driver is 0 to or minus 400 to plus 400, and I'm actually sending 60-ish or minus 60-ish to it to get my speed.
Okay.
So I'm far from maxing out my motor drivers.
Pat, can you zoom in on the falling edge of the first burst?
Yeah, so I'm gonna zoom in on this guy, and so you can see there a little bit of lag as I'm going up when I slew my input, and I'm just hovering above and below the line. the green line to the red line, I'm out about a pulse on my encoder for speed. So one pulse either way makes a difference. And I'm trying to work on that. I've got 32 pulses per rotation of the motor right now, and I'm looking at doubling that to 64. On the falling edge, I don't know if that's zoomed in enough for you guys. Maybe I can bring it in a little more. So on the falling edge, as I go down to my set point towards 0, there is still a little bit of a lag on the green. And what looks to be a big overshoot on the output on the blue doesn't seem to be making a huge difference on the green. As you can see, my green falls into place within about 150 milliseconds, let's say, from here to here of my slew coming down to 0.
It's interesting that you actually have found here what I was looking for last month, which is does the output of the PID controller actually go negative when it's trying to pull the velocity down to 0? And it does.
It does. And so there is the occasion where I keep screwing this up with a right click to zoom in. And there is the occasion where I will overshoot a little bit, and you'll see the green pick up, and it'll pick up a couple centimeters as a spike in the opposite direction, and then settles down. And that's happening, okay, and enough. I'm not super concerned with it, but it is happening. You can see it, as well as you can see the blue. My output will, as it's going positive, will overshoot, comes back, undershoots a little bit, and then dampens out.
Pat, you know what's called a critical damping? Is that a term familiar to you?
I've heard it before, but
think about any kind of oscillating system like a bell or something like that.
Yeah.
The standard terminology is that it can be overdamped or underdamped or critically damped. And generally critically damped is considered the ideal, although as we've talked about before, a lot of it is aesthetics, you know, how you want your robot to behave. Can you see my hand here? Let's see.
Oh, I can stop sharing. Hang on.
Well, you don't necessarily. I'll do it horizontally. If something is critically damped, basically when it comes to a stop, it overshoots, corrects, and stops. So, as a matter of fact, if you move your own hand fast, you can see it does the same thing. If you try to bring it to a stop, when you move it quickly, it overshoots, corrects, and stops. So that's kind of considered the ideal behavior, and it's what you have there. Overdamped means that it won't overshoot, but it also probably won't make it to the set point. So it's kind of mushy. And underdamped means that basically it won't stop oscillating, or it takes a long while to stop oscillating. So if I understand your graph correctly, it looks like you have it set for a critically damped function, which is what you want. You can
That's basically what I was aiming for. And there's occasionally it'll go into a second wave, like a second overshoot before it settles out. But for the most part, that's what I'm seeing. Now, I haven't grabbed any while it's moving on the floor yet. So that's going to be my next step, is just to see how it reacts with a load.
Very good.
So that's about it for me, guys.
Do we get to see the other wheel?
Oh, you want to see the other wheel? Sure. So that was the one wheel. And I believe this is my other wheel. So you can see it's not quite as good.
Interesting. Well, you still see those things. They're overshooting, correcting, and then coming to a stop.
Yep.
Which is what you want. What is your what's the interval here between the sample points?
I am at 50 milliseconds.
So there's 20 of these per second?
Yeah.
Yeah, it almost looks like it's underdamped because on the positive part of the pulse, it kind of goes up, and then you can kind of see like an oscillation or a little bit of a sine wave there.
On the positive port, you
Yeah.
mean here?
No, in the blue. Well, and in the green.
Yeah.
It kind of follows the blue.
Yeah. So here the problem I'm having, if I can zoom in again. So here my change in my pulses are just 1 or 2 pulses on my encoder to give me this reaction. And that's where I think I don't have enough counts. So I've got 32 pulses per rotation of the motor, and it's 50-to-1 gear ratio.
So how many ticks do you get at full speed?
So at full speed, I believe I'm getting 1,600 per wheel revolution right now.
And how many is that per second?
It is per second.
Okay, how many per 50 milliseconds?
Per 50 milliseconds, it would be.
Your timing is for your pit loop.
Yeah, I never stopped to actually think about it.
Pat, you were mentioning, when you think about that, you were mentioning that your green line is oscillating by ±1, and how that might mean that you don't have enough pulses. But I'd make another argument that says, if you're able to control it within the LSB or the nearest encoder tick, then you're doing just fine.
Yeah, well, that's when I'm looking at it. I am getting. I thought it was 30, 31, 32 pulses per revolution, or per not tick, but per scan loop. So it's not a lot, and that's why I wanted to try to double it. So right now I'm triggering on A phase on my encoder, and I'm reading B phase to give me a direction. But I think what I'll do is I'll write a second interrupt routine from my B phase and do the same thing. So I still can get a direction with the encoder ticks. So I'll just double my pulses.
You can, Pat, trigger on, or at least some hardware allows you to trigger on both the rising and falling edge, so you can get 4 times.
Well, that's what I'm doing right now. I'm triggering on the rising and falling edge of A phase.
I see. So you can double that by triggering on the rising and falling edge of B phase.
Yeah, so if I create a B phase interrupt routine, then I can trigger off of that as well.
Just as a kind of a rule of thumb, I found that it's useful to figure out if you have enough coder counts to run 1/10 full speed. So if you got 60 counts per 50 milliseconds at full speed, that would be 6 counts per 50 milliseconds at 10th speed. That's kind of a handy number to have.
Okay. And that's when I bought the Polulu motors. I'm pretty much stuck with what they have for the magnetic encoder on the back. I wish I could have went to an optical with more.
I think you have plenty.
Okay, I'll give it a try anyway with doubling, going to basically watching all 4 edges as it goes.
If you don't have enough counts, where it'll show up is when you're trying to go really slowly. It'll kind of jerk because you don't have. Imagine that you only had 3 counts, so you can be a third too high or a third too low. So the control tends to jump around.
Yeah.
But you'll see that, and if you don't see that, you're good. Sometimes the momentum and weight of the robot itself will smooth that out.
Well, and I do have a fair amount of weight on the robot.
And Pat, you've got somewhere between 3 and 4 times as many ticks as I do on my robot, and I haven't seen any problems. I think you should be fine.
We'll see how it goes. Like I say, this week, hopefully I'll get the chance to, if work doesn't interfere too much, I'll get a chance to try it on the floor.
Well,
You
guys,
mentioned
would you
that you were
say
using Pellew motors.
I didn't catch that, Doug.
You mentioned that you were using the Pellew motors. Are those the 12 volts?
Yeah, the 12-volt gear motors.
So,
They're 37D 12-volt gear motors.
so how much voltage is your battery sending to the motor driver? Using
12
them?
volts with pulse width modulation. I send full battery voltage.
How much is
My-
full battery?
12 volts.
Oh, okay. Well, darn it. I've been having trouble with my robot, and I was sending 12 volts to the L289N or whatever that is.
Yeah.
And the motors weren't doing anything, so I thought I needed to bump it up because I'd been told that it drops voltage and was only given like 10.5 to the motors.
There's another thing you can do with those, and it's change the pulse width modulation frequency. And there's articles on the net about changing the frequency if your motor isn't reacting.
Yeah. Okay. Just a
That'll-
question.
That'll also help if you run into a case where the motor doesn't start turning until you're, say, 30 or 40% PWM. That's often a problem with your frequency, the PWM frequency. It's a combination of the PWM frequency and the resonant frequency of the motor itself.
Which way would you go with that, David?
Oh, I'd probably just arbitrarily turn it up and see if it made it better or worse.
That's what I'm wondering. I forget what the default on the Arduino is for pulse width modulation frequency. If it's 2 kilohertz or something like that.
You know, often they try to put that up out of the audio range because it's annoying to have this, this 2 kilohertz signal, which is what? I mean, that's still on the piano keyboard. So often you'll see it at 20 kilohertz or higher, just so that you can't hear it.
Yeah.
But I've also had systems that had to run much lower than that.
And that's, to me, the closer you get to DC, the more current you'd be holding longer in a winding to magnetize a motor. And that's just my electrical theory coming through. So I'm not sure about if I increase the frequency, if it'll get better, or if I lower the frequency, will it get better?
Yeah, try both.
Yeah, in Arduino land, I think pins 5 and 6 are 980 hertz. And just about all the other ones, like on a Mega 2 through 13, 44 through 46 are 490 hertz. So it's pretty low. I was going to ask if I guess if you don't have enough encoder bits, it may look like they're under damped.
Well, that's a good point.
Yeah.
Maybe not really under damped, but kind of.
Well, it's just software to double the pulses, so I'll work on that first. Okay, that's it for me.
Hey Pat, just in one aside, I'm just curious, what's your gearhead ratio?
It's 50 to 1.
2 to 1. Yeah. I don't really see. I mean, I've used the 37s and I've used the 25s, and I've never had any problems with not having enough pulses with a Pellew motor. If you really crawl it, you might get into the point where, like, you won't ever get down to 3, but you might be down at 6 or 7 if you're really going super slow.
So at 30 centimeters per second, I'm less than 1 wheel revolution.
What? What are you?
I've got 6-inch wheels on there.
Oh, well, that is. Yeah, but you're going 30 millimeters, right? I mean,
30
centimeters.
centimeters, about a foot.
Yeah.
But, yeah.
Okay. Well, that's almost a yard a second.
No,
Yeah.
I'm going 30 centimeters, 1 foot per second.
30 centimeters.
Miles per hour.
Okay. All right. I'm sorry. I got mixed up in my metric. Okay. Yeah.
Well, it's also the case that when you're going really slowly, there's two issues here, and we've talked about this before. if you're using differential drive to steer, that means the inside wheel has to go slowly, and it has to go slowly at a very precise rate. So how slowly you can drive the robot translates into how precisely you can control it. On the other hand, if you're just driving in a straight line, you're probably either, if you're going that slow, you're probably either coming to a stop or starting off, and it really doesn't matter that much. It doesn't need to be that precise. As I say, the precision starts to come in when you're trying to steer.
I can also get velocity looking at the time between the rising and the falling edge on the pulses. And I can do that in my interrupt service routine and grab the distances, and I store them, and then I just calculate it out to whenever I get to the loop, what was the last speed. The problem I do with that is I don't get a direction.
I don't really think that's necessary. I think you've got enough ticks.
Yeah, it's just a matter of figuring it out. Well, what I'm doing right now is on a turn, I speed up one wheel and I slow down the other wheel.
Exactly.
So
that way the center of the robot maintains a constant velocity.
Yeah, and that's basically what I'm trying to do. I haven't limited it yet, but it depends how it'll work in real life.
Cool.
So that's 0.681 miles per hour. It's pretty fast.
Is that fast? Because I could easily triple it.
There you go.
Cool. Well, nicely done, and hopefully next time nobody translates their numbers into angstroms per fortnight. But
The one that's giving me trouble is radians.
Radians, yeah.
Oh yeah, 70% of electricians are mathematically illiterate. Almost half of us.
I like radians.
Oh, they're driving me nuts.
Chris was complaining recently that, it's like if you say turn 90 degrees, everybody knows what you mean. But if you say turn pi over 2, nobody knows what you mean.
Yeah, that's just not intuitive.
And Americans like pie.
A la
And
mode.
then you've got quaternions, which are even worse.
Oh boy.
Quaternions.
That's a
Alrighty,
Star
I think
term.
Quaternions are a better way of doing Euler angles, because Euler angles have these weird singularities in them, and quaternions don't. But basically, it's a vector and then a rotation around that vector, and that my eyes glaze over.
I thought the Quaternions are the ones who destroyed the Klingon Empire.
They did it with math.
Yeah.
nice.
Bored those Klingons to death.
All right, so looks like we've got some Team Kareem, some Iron Rain guys all queued up, I'd say. Although maybe stepped away from the camera for the moment. Is anybody there?
Hello, we're here.
Cool. Well, if you like, I would say this is your turn. You can jump right in.
Okay, so we'd like to share our I don't know what to call this robot. It's just a ridiculous mess, honestly.
Circus bot.
What?
Circus bot.
Circus bot. What? Okay. Anyway, we're Iron Rain. On the cameras, the microphones today, there's me. I am Trey Davis. There's Paul. Cooper is coding, and then of course Mr. Ronnie Kareem. Yeah. Here I'm gonna go ahead and share our model just as a quick preview. We have a physical robot here. Window. That would help. So this is our robot. It's kind of a morph between like a standard differential robot drive assembly and like a swerve robot. So we have a swerve wheel back here and 2 differentials up front. But the only difference is that it's very long and that it expands out back and forth. So we have our back kind of differential. Actually, this is the front of the robot. We have our front differential wheels that are connected to the swerve wheel that turns. It will turn. It won't turn. Okay. That turns 360 degrees here on the back of the robot. And the idea is that we would have one arm all the way back here. one arm back here, and another arm up front. And so we would be able to grab little blocks and objects on the front and then pass them to the back and have the robot like shrink and expand throughout our competition. Yeah. I think we have a couple calculations and things that Ben can show.
Yeah, you guys also have the physical robot there. I don't know if you can show it to the camera
Oh.
briefly.
Sure.
I just got a text saying that the robot's busted, so I'm not quite sure what that means, but
Yeah, I can move the camera.
all right, we
The motor has had 10 minutes to push code to a robot that was in separate parts about 15, 20 minutes ago.
An hour ago, 20 minutes ago.
All right, full hour spin.
You've had a full hour.
Yeah, I like those odds.
And the code's just not working yet.
Oh, yeah.
Gee.
Wonder why.
Yeah.
okay. So I can show you some of the calculations behind.
Ben, can I ask a question here? The reason for having the base extend is because you have a limit of 18 inches when you get started. Is that correct?
Yeah,
That's one of the reasons, but another reason that we're having it extend and so it can move on its own is so that both halves of the robot can be doing something at the same time. So the front half of the robot with the two wheels can be performing a task at one end, while the other end of the robot can be moving around with its own claw or arm, doing something else.
So a match is only 2 minutes and 30 seconds. So you're actually trying to maximize your points per second. And so if your robot can do two things simultaneously legally, it could be a competitive advantage. But it's a real reach what they're trying to do. So their first tournament is on the 11th of December, and
He calls it a reach.
It's going to be a nightmare. There's no way that the code can be working by then.
Yeah, it's gonna be a nightmare.
Hey.
Hey.
And I don't think anyone's even practiced driving the robot.
Yeah, well, welcome to the real world.
11 days. Who needs to sleep?
Yeah,
Literally, this is the first time they got all three wheels on the same frame, right? As of like literally an hour ago.
You could have left that detail out.
I would say that in some companies, that's when you decide to ship it.
Oh.
So they're making a lot of progress.
Moving? Are they going to get a gold star?
Gold star.
It's moving.
First of the evening.
Now extend the frame. I want to see that thing, expanding it. Oh, wow.
That's just as good as your camera, Chris.
You put a skin on it like a caterpillar.
When you were driving it just then, were you driving all three motors?
I think he's driving just. The swerve motor right now.
Just the swerve. Okay.
Jack's squat right now. Just stop working.
Oh, just died?
Yeah.
Power's off. No.
Power's on. Lights on.
All right. I don't see the green light. Okay.
So in play, it will extend by moving that swerve wheel at a different speed. So it's just on linear rails.
Oh, really?
I fucking hate this thing.
Control hook? Driver hook?
So to be clear, the rails aren't motorized in any way. You just choose to move the wheels at different rates.
Correct.
Yep.
Correct.
Yeah.
Can you lock it into a certain position once it's in a position?
There's no physical lock, but we could just move that swerve wheel at the same speed as the front two wheels, and it should stay.
Yeah, we did test that. We did test having a lock, but we just really want to be able to expand and contract throughout the entire match.
Gotcha.
Welcome to take time and add complexity.
That's why it's a lock. Yeah.
But if there were style points, you could put it in inchworm mode.
Put a brake on the wheel.
Okay, and you guys have some way to measure the distance between the center of the two wheels and the center of the swerve wheel?
Cooper.
What? I'm actually like Yeah, what's up? Sorry.
There's going to be a distance sensor that actually uses a laser distance sensor to determine what the changing length is.
Hello.
But
Yeah.
it's not on there yet.
It's not on there yet, but
working
how
on it.
we've got our calculator set up in our class structure, we should be able to, every time we update the values for the requested like new position, and we'll get into the calculator, it will update the length of the robot to pass into the calculator. So it's like dynamic and whatnot.
Yeah, so here's a look at the Desmos calculator that we created to kind of model this robot. You can see it's a triangle like the robot. These front 2 points on the triangles are the front wheels, and these will always stay an equidistant from each other. They won't change at all relative to each other, but this bottom wheel, we refer to it as wheel C, will change horizontally. And that can also be modeled, I can show you, or I'm sorry, vertically. So it can go different distances from the center point of the front 2 wheels, and eventually someday maybe horizontally, but I'm not the one building it, so who knows. But this is basically how we calculate how each wheel needs to behave or move in order to get to a new position. So it's basically just a bunch of like geometric displacements. So we developed this calculator so that you can visualize how it needs to move. These are distances that each wheel needs to drive in order to get to the new location. The green triangle is the original location, and the orange one is the new location. The purple line is the displacement line. So from the center of wheels A and B to the center of the new position for wheels A and B. There's also a angle from the vertical that the wheel C will need to rotate to in order to get to this position as well. And that can be seen here at the bottom.
It's going to act like it's not. It like is so finicky, it's actually. We're talking amongst ourselves, sorry.
I guess you could say this project is a bit of a reach. Get it? That's my only contribution to it.
That's nice.
You see why it's a circus now?
So Reach is the working name for the robot.
Oh, is that the name? Okay.
Oh, it's Gilk.
Sure.
Gilk?
Gilk?
No.
Where did Gilk come from?
Ben and I.
Okay.
You know Gilk history? You know,
Oh, no.
What?
You know Gatorade powder?
Yeah.
Yeah. Do you know milk?
Oh, no.
So, are there any questions about the calculator, the robot, instead of talking about Gatorade and milk?
So how are you, like, what questions is this calculator answering for you? How are you using it?
So it's basically just going to be transferred into code. So it's calculating the displacement of each wheel, and then I believe that's turned into like an angular velocity. I think Cooper can talk a little bit more on that. Cooper. Cooper's
Cooper's probably focused on code at the moment.
Yes, hi.
Okay.
What's up?
Okay, Cooper, how is distance converted to angular velocity for the motor?
Oh, okay, so all we do, it's really rather simple. So we take the distance that's spit out for each, like the distance traveled for each one of those wheels, and then you divide that by a normalized loop time so that you get a meters per second, so a linear speed for each motor, right? And then you can divide that by the wheel radius, because angular velocity is equal to, isn't it linear velocity times radius, right? So then, no, angular velocity is the linear velocity over the radius. I failed physics 1. So yeah, you divide that speed by the radius, which gets you an angular velocity. And in the implementation of the motor class, in the SDK we're using, there is an advanced motor class that allows you to like simply set angular velocity directly to the motors, and it has low-level PID that it does all of its own stuff, so we don't even have to, mess with it.
Yeah, and it's funny that we were just talking about radians earlier, not knowing how to do radians, because this calculator's in degrees, because that was just what I naturally went to instead of radians. So, and it actually uses radians in the code. So.
Math is hard.
It is. It is very.
One thing you might want to be careful about is that sometimes controllers, if you write, as you described, an angular distance, there's some delay as it does that. So it's not instantaneous, and that may affect your behaviors.
Can you say that again? Sorry.
If you're depending on the controller to give you angular distance, that is, as was just described, sometimes there's a delay in that, so that it's not instantaneous with the instruction.
It should be encoded though, right? So it should be telling the exact contribution effectively.
What?
Oh no.
We're
in a meeting.
Sorry. I'm trying to get it working for y'all. Could you repeat? I'm very sorry.
Control same things that we have encoders though, so to be able to compensate for that.
Yeah, we've got. I don't know if encoders would help you compensate for that, but we do have a normalized loop time. So, and it's pretty consistent. It's not like changing all too much. So taking the previous loop time is not. Yeah, it's not like particularly a bad thing, but I agree that there is like inherently delay, but it's nothing. It's nothing logically that should make a difference. But I will keep that in my back pocket when I realize that it is broken.
So, but you've already considered that, so that's good.
Yes.
So, what are the big questions and challenges you're working on for the next few steps?
Right now, in terms of how the robot is built, we're still missing a second stage. So it's figuring out how to manufacture all of the plates that link these stages together, because this is a really compact space, and we're trying to put two really flimsy pieces of metal together with very little space, and so that's kind of a design challenge at the moment. Another design challenge that we're having is that these chains they're a little bit, they're janky. They're not great. They're a little loose. They might pop off in competition. So those are some of the things we're working on as of now. What?
Rigidity.
Yeah, rigidity too.
It's wiggly.
Well, we're also working on designing arms to interface with the field, so we can actually pick up the elements. Because right now it's just a push bot, just pushes stuff around.
Yeah, there's also a project we were working on with motors. So because wheel C covers a much larger distance than the back two wheels, we were trying to figure out if we're using the best motors for them. And so that means figuring out how we can vary the gearbox on those motors to make sure that the wheels at the back end up having more torque, whereas the wheel at the front has less torque but more speed.
I was going to ask about this one part of the robot. It's long and narrow, and you're going to add arms at both ends. And it struck me that the robot is not very wide. And I was just thinking, in terms of center of gravity, it sounds like it'd be very likely that the robot might just tip over. Have you thought about maybe widening it a little bit?
Yes, we have thought about that. It is a bit of a design challenge for the time being, but especially after our first competition, we did thinking about having these two rails on pivots so that, well, actually, yeah, it would be more complicated than that, but basically that's kind of what it would do. So it would expand like that, and then it would be absolutely massive.
The problem is we also have
The arms that we're planning to manufacture to sit on top will be made out of like carbon fiber and just a 3D printed nylon. So it won't be made out of like the same aluminum, which is a little bit heavier. So
And the things
it
you're
should be
picking
fine.
up, and the things you're picking up are not very heavy.
Right, just like plastic cubes and plastic balls. And we'll also have the weight of the battery and the control hub and all that to keep it on the ground as well.
That would look awesome if it could expand and contract in both dimensions.
That's, we have implemented that on our graph, on our Desmos calculator. So maybe someday, Trey.
I have a life, a family.
So is it the case that sort of conceptually you're thinking of this as two separate robots, each with its own arm?
Yes, and that comes with the challenge of having to have two drivers as well.
Yeah, each controller will control each side of the robot. So one person will be controlling the swerve wheel and its arm, and the other person will be controlling these back two wheels. So yeah, it is much like two robots that are linked together rigidly.
Does that mean you need to recruit twins?
Yeah.
It's like the movie Pacific Rim.
Lots of driver practice, more so than previous years.
In 11 days.
Yep.
You know what? We've had days with zero driver or competitions with zero driver practice. So this could be.
And this is gonna be one of them. So
Look at what you've accomplished in the last hour. You could make 5 of these in the next 10 days.
Oh, if we were selling this to a customer as a product, that would be messy.
That would be very messy. That would be a lot of emails.
A lot of paperwork to fill out.
So is your end goal here that you want to have the robot autonomously be able to figure out the velocities and angles that it needs to drive through, or will that always be done by humans?
Sorry, could you repeat that?
I'm not gonna make you repeat it. So
Ben can answer that.
Partially, it will some of the time. So the field won't always be the same. The elements will be in different places throughout the field. So there are times when the drivers will have to manually adjust the angle of each wheel. But when it's driving or moving across the field, or there's actually a minute-long autonomous period where the robot will be doing things on its own and parts of the field will be the same. So in that case, it will use like an optimized path for every wheel. But during the teleop period, most of the time the drivers will be making their own adjustments to each wheel.
No, I can't. That's not right.
Okay, just kidding.
That's what sure? that is what they have to do probably for this first competition. Maybe because they have that Desmos Calculator is basically a kinematic model for the robot, right? And what the drivers are going to be doing is saying, I want the robot to be so long, or I want this portion to be closer to a certain location on the field. But the kinematic models has to enforce consistency that all of those things match, right? So at any point in time, I'm pretty sure that they're going to decide one driver has more control than the other in terms of like what's the actual field position of the robot, whereas maybe the other driver has more control over the angle, perhaps. But the kinematic model is going to have to enforce all of that. Otherwise, the robot's just going to start waggling around and doing, and it'll be very, very, very floppy.
Then it will tip over.
Yeah. So the drivers are just asking for desired locations and positions and arrangements, but the kinematic model sort of has to limit what it's going to deliver.
Well, it will certainly like adjust the speed of each wheel, so it stays the same.
Does that. So it's basically calculating vectors, right? That's the way you've got it set up, Ben. And so however the drivers ask it to reconfigure, it has to go through that to come up with a consistent solution.
Well, let me give an example. Suppose that the back two wheels are driving at an arc, so one of them is a little faster than the other, and then the front wheel at that point needs to be turned at an angle to match that arc and at the proper speed. So suppose it's not at the right angle to match that arc. Basically, in that case, the rear wheels will push it and make it slide, right? So is that the thing that's going to be constrained kinematically? That is, that you're not allowed to put it into that configuration?
Yeah, that's correct. You can't put in a configuration where the vectors for the wheels do not match what is not going to strain the robot, strain the frame, if that makes sense.
So in that case, you could actually drive the thing from that upper level, right? You don't really need to control the speed and angles of the wheels.
That's correct. You're actually controlling where you want the wheel to be in terms of the field, and the kinematic model will calculate the closest it can get to that desired.
So basically, you're sort of driving it through the kinematic model.
Correct. That is the plan. Right now, the kinematic model has, like what you saw it doing earlier, was more of that direct drive. And so Cooper's working furiously on getting the kinematic model worked out. Not right now, but by our competition date, the kinematic should hopefully be worked out.
No class is safe.
So
I will be working on code.
So if I'm hearing this correctly, then is it so that each driver will basically have the control of one point on the robot, and then they're going to kind of steer where they want that point to move around, and then the kinematic model figures out which speed and angle of which wheel to do to get the points where they want to be?
Okay, one driver inputs a rotation rate and a forward rate, and that translates to a new target position, as you can see in the model, right? So it's only one driver setting one target position based on the input rates.
Well, when we're doing stuff like collecting the elements, there will be someone who controls the front part of the robot and someone who controls the back part of the robot. So yeah, so the back wheel could theoretically be driven separately from the front wheel to take the back of the robot somewhere else.
So it sounds like you'll have a couple different modes then. Because
Yeah.
what I thought I heard there for a while was that, in a way, each operator would have a control, and in my mind's eye, I was hearing that as like one operator would have the control for let's say the rear point or rear gripper, another driver would have the control for the front pointer gripper, and then they would kind of, I'm imagining a little joystick or something, they would describe to the joystick which way they want that point to move around in space. And then the kinematic model, as I was imagining it could, for example, optimize and figure out, well, this driver wants that point to be here, the other driver wants that point to be there. And the way to like get both points the closest would be to use the kinematic model and maneuver this way or that way. Mm-hmm. In other words, to really decouple from the operator's joystick, if you will, from what the motors are doing.
Yeah, that would be nice to just have the robot move where you need the claw to be. But the issue is we really need manual control of the position on the field because there are 3 other robots there too. So if we just have the robot move based on where the claw needs to be, like if we're just controlling the claw, then it's possible that the model will take us to an area with another robot or into the path of another robot.
And the sensing of those other robots basically is you, right?
Yes. It's kind of like I know that there's some fire trucks that are driven by two drivers. So there's someone who will drive the front of the truck, because it's so long, there's like a way to like kind of like curve the truck from the back. So there's someone on the back who drives the back half and someone on the front who drives the front half, and that's kind of what this robot would be like.
But
when we were out in Seattle, we saw a Boeing airplane wing that was hooked up like that, with one on one end and another on the other end, and so they're having, I guess they could talk to each other. I always wondered how they communicated, but allowed them to do things like get off the highway and turn a sharp corner and so forth. The guy in the back, actually, the wing was mounted over the top of his cab, and so he's looking out underneath the wing so he could see the forward. But now in their case, they're not changing the distance, right? The distance remains fixed. That seems like the big potential gotcha here. I'm having a hard time getting my head around it.
So the reason why we may need the distance to change is we have to pick up the elements at one spot and take them to another. So there's going to be a handoff between the claw on one end of the robot and the claw on the other end of the robot. So for it to get from one claw to another, it'll have to close the distance between them for the handoff, and then extend back to deposit it at the location where it needs to be dropped off. So that's kind of why it extends. And maybe we're on a different position in the field, and it doesn't need to be quite all the way extended to reach the part where it needs to be dropped off. So there's a couple different scenarios where having a variable length of the robot could be helpful.
And at this point in the process, that decision will be made by y'all, right?
I mean, eventually it would be nice to just, based on the position of the robot on the field, calculate automatically the distance that needs to retract and do an automatic handoff and like deposit the element. But at this stage right now, that will be all done manually.
Does a single person work the steering for one end and its claw, or do you have like two wheel movers and two crane or claw movers?
So we're limited to only two controllers. We can only have two controllers. So how I think Cooper's setting it up now is one person will control the front half, the claw and the wheels, and another person will control the back half, that claw and that wheel.
Okay.
Ben, have you actually tried this?
No, I have not even touched the robot. Well, okay, it was just built tonight. So
Given that, but I mean having two different drivers to drive in.
Last year, our robot had two pilots. So we have worked on that before, and there's always issues with driver communication, but through practice, I think we could probably get our routine down.
And these two drivers are standing right next to each other. Right?
Yes.
So they can say, no, left.
Yeah. What are you doing? What are you doing?
So they I'll have to designate one of them as the backseat driver.
Coordination is going to be a huge challenge. There's no doubt about it.
Hire a married couple.
Oh boy. Now I'm thinking of the tandem road cycles, and those are known as either a way to make or severely break a marriage. So,
Murray, you can't make those jokes yet.
I know, sorry.
We have a very big confidence boost, and I'm looking forward to driving that thing.
Well, it's a really impressive design. I think you guys are, even if it doesn't work, it's still a very impressive try.
Looks
it's
cool.
a reach, right?
Oh.
Oh, David, you're muted.
Closer.
I was saying, I think you're going about it right. You already have the kinematic model, and because you're going to start off with two human drivers, a lot of those other problems can be at least sidestepped initially.
Yes,
Well,
there are
appreciate
a lot
your
of
time.
things. Okay.
Sorry, go ahead, Ben.
I was just going to say, there are a lot of things that we would eventually like to automate, like the distances based on the position on the field and stuff like that. But for now, I think we have 11 days. We need to prioritize getting it moving before all that stuff. So.
By the end of the season, the hope is that they'll be driving it from an inverse kinematic model.
Mm.
But the forward kinematics is the first step.
Did somebody just break something?
Yes.
I think Ben just dropped.
That would be on brand for us.
The thing holding my camera on top of my monitor just fell. So.
No. Well, thanks for your time, guys. We really appreciate the input, and we'll be coming back to you with updates and trying to figure out what the real issues that we can't figure out are.
Okay, and the whole group gets a gold star.
All right. David said it. You got it.
Yay. You're gonna have to get a big bucket of gold stars every time you all come on. That's something.
Well, great work, guys. A really intriguing idea. So keep
bound to fail, but it's going to be fun.
Keep us updated.
You're going to enjoy it, and we're going to enjoy watching along and cheering you on. So come back as often as you want.
All right, cool. Thanks.
Thank you.
Yeah. All right. So So we had next in queue. We have I have something to share. Doug D has something to share. Who can we put on deck after that?
I'm going to need a few minutes before I'm ready. This is Doug D.
Paul. Okay. So maybe we'll go Carl first, then Paul, and then anyone after that. We'll wing it. Okay. Fair enough. So let me jump in. It'll take me just a moment. So I have some. I have a few things to show that are all kind of related. The first is a gripe about the language C. And maybe it's just a personal thing. Maybe there's something there, but I am wondering, I stumbled onto this, and this particular thing, if you can look at this line 777, who can spot the difference?
The double equals versus.
Oh,
equals.
yeah.
Classic,
That cost me
classic
hours.
Classic.
Cost me hours.
There was one. It's a
So-
new.
Here's a technique that I learned, Carl.
Reverse them.
If you want to avoid that problem, put your literal first. It's impossible to get it wrong if your constant is first. You'll get an error because you can't assign a value to a constant.
Say if true equal X, that will generate a compile error. But if true,
and I hate reading code like that, but it will certainly eliminate that problem.
It is a valid gripe. It is probably the worst thing about the C language is that one issue right there. Is it's so hard to see.
Or just leave out the true. You don't need it.
Well, yeah, that's another. If it's Boolean, yeah, that's
So-
another case. But
Okay.
anytime you're comparing to a constant, put the constant first. It looks funny, but it saves you lots of debugging time.
So you're
I
only
would-
reading.
I tend to do what Ted suggested. Just say if did hit cone.
Okay.
If that's 0, then you didn't, and if it's not 0, then you did, and you don't need the equal true.
So I do that at times as well, but everything I'm hearing just reinforces the gripe that I have. So why on earth would this, number one, why on earth would this be allowed in a language in the first place? Is there some reason?
Well, you might actually want to do that. You might actually want to assign something and then branch based on what you assigned.
Yeah, but this doesn't, it looked like as long as there's an assignment there that's valid, it's always going to return true.
Well,
But
in
you
your
also-
case, sure. But what if I had a function there instead of a constant? I would want to assign it to that variable as I go, and it's not that you want to do that necessarily because it's whacked out, but it's something you could do if you needed to.
Well, you're also breaking another principle, and that is you don't want to have a side effect. And so
Yeah.
you want to have separate lines for things that assign
Yeah.
things than things that are functions. And having a side effect where calling a function changes a value is probably not a great idea.
Yeah, okay. And then the next question, so why don't the compilers and linters even give a warning? So I just don't get it. Okay.
The linter should have warned you if you got it twisted up enough.
If you got to
Should have
configure
warned you about
correctly,
that.
It said, "Oh, this is just fine. I'll let you run that," and then it didn't work. So,
Well, to use Harold's example, if you had a function there, you said if did hit cone equal query did I hit cone
Yeah.
parentheses. So you're running a function, you're assigning the output of that function to a variable, and then you're testing to see if that variable is true. See, you see that as a bug. I see it as flexibility.
no, but I see that the result of this test is the result of the assignment, and it seems to me that as long as you
will always be true,
it will always be true.
The assignment will always succeed. So what you can do in that case is you can say something equals to this thing on that assignment, and that way you can get some real funky things going on there.
Yeah. Okay, so this is the bottom line I'm hearing is that just live with it. It's C. Don't write it that way. Just don't do it. Okay.
I have found some
Carl, they haven't
compilers
changed
that
it.
if you
They
turn
haven't
the
changed it
warnings
since
up high enough, they'll give
1970.
you
I
the warning
doubt
on
they're going
that.
to change it for Carl anytime soon. Not that Carl shouldn't be listened to, but
What were you saying, Ted?
I've seen some compilers that if you turn the warnings up high enough, they'll give you a warning on if statements that are always true.
Oh, cool. All right. So I need to look for compiler switches then.
Yeah.
Because I've made that, I seem to make the same damn problem every time I set something aside on this project for like 3 months for surgery or something, and then come back and then I forget it. So it takes another half day to figure it out.
Well, it's the problem that basically we're using the same symbol for both assignment and for conditional.
Right,
and,
right.
And if it wasn't equal, if it was something else, say the letters EQ, like in some languages, you wouldn't make that mistake.
Right, right. Yeah. So it's back to language design, and this thing I learned at CMU where the guy said the language C is named after the grade that it earned as a language. So okay.
Well, actually, it's sort of interesting. A part of me wants to assert that C was the first replacement for assembler, then was designed back in the late 60s. But then I note, though, that Python has the exact same issue. So this issue has existed for a long time.
It's a virus. Okay. It's a language virus.
Well, I think it's the same thing that once a standard is established, it keeps going. Like the spacing between the railroad rails is actually the spacing between the chariot wheels from Roman times.
Based on the spacing of a horse's rear end. Yes.
Exactly. And the size of the old Hollerith card was the same size as a dollar bill in those days.
Really?
Well, you guys remember when gas trucks used to have a sign on the back that said inflammable, because inflammable means the same as flammable.
Hey, Carl, I do know one guy who codes in C, and he does pound defines and makes his own symbol for equals. I think he just uses EQ, and he also pound defines and to be word and stuff like that.
Huh.
It annoys me, but it would fix your problems.
Actually, that's a good
Don't
point.
do that.
With
Don't
Unicode,
do that. I worked with someone once who essentially defined their own language by doing exactly that, and you couldn't read their code.
Well, I also found that if you use the trick where you put the constant first, it annoys the other programmers on your team.
So
yeah, I find it annoying.
So this is it.
So then you need coding standards. At Lockheed, we had a coding standard that said when you're comparing to a constant, put the constant first. And they hash it out in the coding standards group, and then everyone does it.
You know, Paul, the early compilers, in my memory, which is getting worse, were actually just a bunch of macros for the assemblers, right? I mean, that's where compilers came from.
and therein lies the reason it says be careful about griping about something, because it is a storied language, right? It's survived the test of time, and it started for a very good reason, and it served us all well. But anyhow,
Well,
Yeah, it's very easy to hate. It's very easy to hate C.
one of the very first languages was Fortran, and the criteria for the compiler was that assembler programmers should judge the output as being acceptable to come from a assembly coder. And
That's the way I feel about C, Dave.
Yeah.
A good C compiler, the output looks like what you would have done if you'd written it in assembly.
Yeah.
Man, I wish I had saved my Fortran punch cards from college days. Man, that would be fun to show off.
I hope you guys do realize that Fortran is still quite heavily used.
You remember the 027 card punch?
The KP27? Yeah, I think I know what you're talking about. Big, massive machine, chunk, 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 punch those cards out.
I heard
I will say,
programmers are in demand now.
I will say, as I often point out here, that all of these other languages that you're describing, at least today, are all written in C.
Yep.
And that one point you guys made about being able to redefine symbols, now that we have Unicode, you could actually use the Unicode symbol for equality instead. You could redefine it, the equal sign.
You need to look up something called ligatures. Ligatures.
The entire set of mathematical symbols is available in Unicode.
Well, I understand that, but what I'm saying is, if you have a ligature capable font, things like Visual Studio Code, which you're using, understands that equals is indeed the equal sign, and will give you a nice big fat plumpy equals sign there instead. Or if you're doing the arrow stuff, like the equals and a greater than, it understands the lambda there and will give you a nice big picture of a thing. It's still equal, greater than inside your code and when it compiles and all that kind of good stuff. But it looks to you so it's easier to tell what's going on. I do that in my Visual Studio stuff all the time. I haven't done it in code in a while, but because I'm just not into that. I'm not in that mode right now at work. But on my home stuff, when I'm doing it, I set up ligatures all the time. That's what they call them. And those are basically emojis for code.
They're default on, if you're using the Macintosh terminal, actually in Vim, you get those by default.
Mm-hmm. They're actually really cool. I'm digging them. I dig those things.
Hey, Carl, once you make that mistake 10, 20 times, it'll stand out like a sore thumb.
I've made it 10 or 20 times. I've made it 30 or 40 times. It's
Carl, everybody else in the whole crew here looked at that and went, dude, double equals, yo.
Well, but that's only because he called attention to two comparisons. If he had not had both of them up, it would have taken a while.
Yeah, because it's so obvious. Of course it hit the cone. I mean, how could this be wrong? It's so simple, but yeah. Which leads to the next thing. So this one cost the other half of that one day, because I was making changes to, if you remember, duct tape and baling wire from the August Robo-Rama competition. And I've been scratching my head ever since it took second place, trying to figure out how I did that. And I've come to the conclusion that it's because of 10% showing up and 90% luck. So anyhow, so I started to get in here and try and replicate its amazing thrashing success in August. And I was changing the algorithm here and there and doing this and that, and it just wasn't working. And I, line by line, I got rid of all the other stuff, and then I finally got it down to this function, and then I finally started commenting out parts of this function, and I finally figured out that it wasn't working because, can anyone guess why? And the trouble was, it's like imbalanced execution. So basically, the way this robot uses the OpenMV cam, and Well, anyhow, it pumps data over the UART. And if there's UART data available, then it'll parse the integer values. If there's not, then it just sends zeros. So I kept thinking that the problem was down here and the logic downstream, but it turns out that it must be that the timing execution required by these is so long that it was screwing up my 20 millisecond timing loop. So because I had so much space available in the slots, so instead of doing it on every 20 millisecond interrupt, I did it on every fifth one at a time when I wasn't updating the neopixels, and then it magically started to work again. So that was just crazy. I still haven't gotten around to timing it to see just how long it is, but there's something in here that's slow.
Say all that again.
Didn't work because best I can tell, these functions right here are really slow.
So in other words, are you saying your data was coming in faster than you were processing it?
Well, no, I'm saying the time to parse the data was more than my window allowed. So it was still busy parsing this data when the next interrupt came along, and it just screwed up the whole thing.
So Parsint is slow, but what microcontroller are you running in this, and what baud rate?
Oh, it's a mega, and I don't know the baud rate anyhow, but this is after it's been available, right? So it's already.
Yeah.
Yeah, the baud rate doesn't really matter. I guess it determines how often potentially you're doing this, but.
So you're just pulling an integer out of an input stream. Is it ASCII or binary?
Yeah, I don't know.
I think that's ASCII. That, I mean, I'm not 100% sure, but
I think it is.
Yeah, it is because he's parsing it.
Well, parsing an integer out of an ASCII integer out of an input stream should be a trivial task. I don't understand why that should take a long time.
I don't
either. Did you measure it? I mean, Carl, did you measure how long it takes, or is that your hypothesis?
No, that would be too clear and direct. I haven't gotten around to that yet.
But just because there's one byte available on the serial stream doesn't mean all the bytes are available.
Well, that's what I was wondering, if you're actually waiting there for the rest of the string to come in, and that's what the delay is.
Oh, it could be that.
That could be a whole lot more than your interrupt.
Yeah, if it was slower, yeah. So
if those are ASCII, are the lines terminated with a new line?
You know, these are all excellent questions.
No characters have been read for a configurable timeout, or a non-digit is read. So if the timeout defaults to some longer time than your frame rate, and you don't have any ASCII, any alpha characters come in to terminate the parsing, then it would sit there until the timeout, and it would do that for each of these parsints.
Yeah, I think I can. I think I can see your point now. So this was the part that Raj did for me. So I hadn't really. I just accepted it as a black box, and it worked in August. So I wasn't going to argue with it until it got in the way. But this is all it does right here. Is it blah, 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 output? So here we go. It just. However that does it in Python from the OpenMVCam.
Yeah, I kind of experienced that with these little OLED displays. If you write too much, you'll get like past your.
No, but he's pointing at the line you're pointing at is producing that ASCII string, right?
Yeah, that's producing the string that then this thing parses.
But that's just generating one integer in that stream, correct? It's not the whole stream.
Oh, it's the whole string. It's the number one, then it's whatever this integer is, then it's whatever this integer is, then it's putting out 5 values.
And is there a new line on the end of that line?
No, I don't see one. Do you? Unless
but each of those calls pars in is going to wait for a timeout, I think, isn't it?
Well, this is on the. I'm sorry. This code on the left is on the OpenMV cam. So this is generating the data stream. And then once it gets across the serial bus, then the UART picks it up here.
Well, that's why I was asking if there was a new line or something, some other way to determine that you had the whole line before you began the parsing.
I mean, even if there is, he's currently not looking for it, so there could definitely be a synchronization issue in addition to just, another type of timing issue. It does get tricky when you have, because I find myself having to do this sort of thing, right? You guys, I presented on my platform. I have slave microcontrollers pumping out data over the serial port, right? And on the Raspberry Pi, I'm reading it in, and you have to watch out for this kind of synchronization that you might have half of the data that you're looking for, right? So you need to know either you need to do something with a fixed size or have some sort of terminator like a carriage return if it's all meant to be humanly readable. So
The statement serial available.
Last line.
The statement serial available returns the number of bytes that it has.
The UART has a carriage return.
Yeah. So what I'm trying to say is you can.
Oh, there it is. Nice catch, Ted. Look at that.
Yeah.
So it does have that. Not that I don't think we check for it, but it is flushed after everything. And I don't know. This was the mechanism that Roz has used before. I haven't messed with it
but
much.
Doug P's onto something, right? You're sitting in this while loop.
Yeah.
And you're just going to keep sitting in this while loop while data is available. So if the first 5 bytes are available, you're going to go in and try to do some parsing. Then you do a flush. Okay, so I guess what if more data came in, meanwhile, you're throwing it away. So you're not really... So even if part of the data is available, you're going into the while loop and you're going to do a little bit of parsing. You may not see everything, and you're going to run into some timeout because the parsing can't do its parsing. So you really got to wait for the whole line to be there.
So the timeout is 1 second according to the Arduino documentation.
I think
So
the other thing we were relying on, and because don't get confused by the while loop. This was the reference code showing the OpenMV Python software as well as the listener.
Oh yeah, I see on the left your code has just an if, it doesn't have a while. Okay.
Right.
Okay.
So this function is called once every 20 milliseconds. And I believe we knew even the 2 days before Robo Columbus, when we first connected the camera to the Mega, the frame rate of the OpenMV cam was slower than I want to say it was like 10 frames a second versus the 50 hertz loop. I don't remember just how it worked out, but it seemed to come across consistently.
Yeah. So, like I said, I'm doing very similar things, parsing integers out of an ASCII string on my setup. And what I'm doing is I'm first making sure I have received as many bytes as I expect to receive, and when I can, I try to work with fixed length kind of packets, so to speak, or I look for the terminator.
Yeah.
And then when I've received those bytes, then I call the parsing functions, and then then that usually doesn't go wrong. But the way you're doing it is just a lot of room for being out of sync.
Yep.
Yes. Carl, is there an equivalent for the serial available? Is there an equivalent call that would tell you when you have a line available?
I have no idea.
David, if you knew the size of your packet, you could do an if serial dot available equal or greater than or equal to
5
packet size, then it would only kick the parsing off if it had at least that many bits. You might have more, but you would at least have that many.
Well, cool. Thank you for that feedback. That tells me I got to work on the interprocessor communications.
Yeah.
Now, one more comment I wanted to throw out. I mean, because in this kind of situation, you're waiting for data and it's coming in at whatever rate, and that's where something like an RTOS, which, however simple, right, can help you, because you can do this receiving of data in one task, and you do it at the rate at which the data comes in, and then you tell the other task, okay, data has come in. It just sometimes makes it a little easier when you're able to decouple things like that through separate tasks. It has its own gotchas, of course. It's it's another rabbit hole, but it can make life a little easier. And if you're running on Mega, you have just enough RAM to run free RTOS. On anything smaller, it's kind of not really practical. You just don't have enough RAM. It just really doesn't want to work. But on the Mega, you have, I don't know what else you're doing and what's consuming the RAM, and that's kind of the most precious resource usually in my experience. But you could potentially run free RTOS and make things a little easier that way.
The other thing you need to check is the serial.flush. It might not be doing what you think it's doing, because it's usually originally it used to be what you would think of flush. It would just flush the buffer. But now in Arduino, I believe the flush looks for the if you have a completed output, enough for an output. So I don't remember the details, but flush may not be doing what you think it's doing. So that's another thing you need to take a look. You got to look at the serial, Arduino serial documentation pretty carefully. I guess that's the only thing I wanted to say on that.
I would add, I concur with Chris that if you're running an RTOS, which is what I do, a lot of those problems of synchronization get a lot easier. Now that may be a bigger rabbit hole than you want to go down. There's another alternative to that, which I've had to do in a couple of cases where I had a big data structure coming in, and that's basically to drive the parser from the interrupt itself. So the parser is a state machine, and each time the interrupt says, I got a byte, it says, well, that's byte number 3, and this is what I do with byte number 3. So the interrupt itself does the parsing as the data is received. But again, that's just another way of trying to get around that same problem.
Yeah, it smacks of two things.
You might want to mention David's LX too. I mean, if you can't, a Mega can definitely handle David's LX system.
That stands for lightweight multitasking executive.
Yeah, and it can definitely handle that. We've done that before in the past.
But I have no allegiance to the Mega. It's just what I've been running so far. I'm pretty sure that next year I'm going to be playing around with expressive, ESP32 and maybe the NRF chips, just because I have some, they're a bit more capable, I think, than Arduinos, and they have nice wireless connectivity built in.
Did you see that part that Murray dug up?
Yeah, I was just going to ask about that. It's called the STM32 MP157, and it's a combination board that has a Cortex A7 running at 800 megahertz and a Cortex M7 running at 209. And so it's basically a Linux processor, STM32 Linux, and an MCU on the same board from ST.
I don't think those are just on the same board. I think they're the same silicon.
Yeah,
I think you're correct. Yes.
It's just an A7. I don't think it has a second core, does it? Like, it doesn't have an M4 or M3 coprocessor. I mean, some of those parts do. I'm actually familiar with the part because we came across it at work doing research for some new stuff. But the board strikes me as, well, not inexpensive, and in my experience, these kind of things are a little underpowered for Linux. I mean, if you're going to run Linux on it, and you're running at 700, 800 megahertz, you're like in Raspberry Pi Zero kind of territory, or original Raspberry Pi, and you're just not getting the full value out of running Linux in my experience. opinion. If you're
Yeah,
on,
I mean,
if you're doing something bare metal on it, which mean they probably have stuff available, right? So you're just treating it as a microcontroller on steroids, then you're gonna get probably a lot of performance out of it. But it's a lot of I/O. That's the good news. But still, $75. It's pretty hefty.
yeah, I mean, it's not a cheap board, but on the other hand, having the integration between those two processors on the same board does seem like, with all that I/O, it seems very appealing.
Let me make a comment about all that I/O. On the ARM processors, if you have a list of all the different functions available, you think, wow, everything I'd ever want to do. What's not obvious is that each time you use one of those functions, you now have removed the possibility of using other functions. So if they say, oh, we've got 16 timers and we've got 3 channels of PWM, well, that's not true. If you use all 16 timers, you don't have any PWM.
You're right. I mean, we run into that problem at work all the time. You run out of pins, to put those. You run out of pins to route the UART to that you want. You want this 4th UART or this other CAN port, and you can't get all possible permutations. So it's definitely a gotcha, and it actually is a lot more painful to sort of set things up so that you get access to all the things that you need access to. But
each one of the functions has what are called alternate. And that's cool, but it's not unlimited. In other words, UART3 can use these 2 pins, or it can use these 2 pins, or it can use these 2 pins, but that's all. And so laying it out is very much of a puzzle. Okay, well, let's see, I can move over this encoder to this other timer, and then that makes this timer available because it's the only one that can drive I²C on these 2 pins, which are the only 2 pins I have available. It's quite a puzzle to get it all set up the way you want. And as I say, you can't just read down the spec list and say, look at all the stuff I got, because
I
each time you
that.
use something, they go away.
Well, and the alternative to this would be, go ahead, Dave.
Fortunately, ST Micro has their handy dandy Cube MX that lets you set up stuff and shows you what has been used up and where to move it and what have you. So it helps in that puzzle.
And I believe that Cube application only runs on Windows, though, doesn't it?
I disagree 100%.
Oh.
I'm running it on Linux.
Oh, okay, all right.
As we speak?
I have a version of it. You want me to open it up?
Sure.
No, I'll take your word for it. I mean, the alternate, put it this way, what I'm looking at, this is a $70 or 109 New Zealand dollar board, so it's not cheap. The alternative to this would be running some kind of a Pi and a Pi board. And I'm really sold on the Pi board at this point. It's got lots of I/O, and it has a MicroPython OS, which has already got all the code installed for running MicroPython. So it's really nice. And so I'm looking at an alternative to the Pi board combination, and this looks appealing because of its integration, not because it gives me a lot more pins or anything like that. And I don't need any more pins. It's simply the integration and the fact that it's one board.
My suspicion is whoever said previously that it wouldn't do either one of those. My suspicion is you'd be happier with a Pi and a daughter board.
Okay.
But that's just my suspicion.
No, and it's less complicated. I mean, it's in some ways there's a complication that comes with this board, obviously.
Yeah, and then there's the 02, and that's the 02W now, which gives you about 3 plus formats with a lot less power. So I mean, that's another option that's just becoming available for most people. I've got one. I'm sure everybody else.
I have one. They only have a half a gig of memory, though. That's the only problem with those.
but
four cores, but
yeah.
640K ought to be enough for anyone.
Yeah.
Yeah, we've reached the point where we're talking about microcontrollers that are, this big, and we're saying, and it only has half a gig of RAM.
Yeah, what a wimpy wussy thing. That's what's become of us. Okay, one more wimpy thing, and I'm going to derail. I'm going to stop being a distraction here. So this is duct tape and baling wire back again. And here we go. After I found and fixed those couple of things, I set it up so it just bounced between two cones, and it's not very good at slow speed, so it doesn't really touch. It goes until the cone is a certain size. But I got it to back up and turn around, and yeah, then it kind of loses things. I've got some more work to do on it. Here's another run of it.
Gold star.
You know,
Yeah, very
I feel
nice.
good about it. It's actually doing something for as sloppy of a chassis as it is. It saw that and backed up really soon, but anyhow.
You were talking about the frame rates you're getting from OpenMV. So what was that? What are you getting here for this?
I'm sorry, what's the question about?
What frame rate you're getting out of OpenMV?
I haven't looked at it lately, but I remember before I went to Pittsburgh in August, the day before the contest, I want to say that it was doing 10 and 15 frames per second. And that was in actually running his algorithm at pretty close to the full 5 megapixel frame size. And we did it that way specifically because we didn't know how well it would drive straight over such a long distance. So we wanted it to be able to detect a really small cone. So so he had it run with pretty much the full frame rate. And the funny thing is that I knew before we left, I knew that you know, when it can't see the cone, it should be following the IMU. When it can see the cone, it should be following the cone and not the IMU. But funny thing happened, and that second part we never took care of. So when I got this part working again, and this is what you see, I think, on the return runs sometimes. At some point, the command from the cone to the steering is kind of like fixed, but the PID loop from the IMU just keeps growing and growing, and pretty soon it overtakes the command from the cone. And that's why, like, a lot of times it gets towards the end and then it just veers away at the last minute because the two loops are fighting each other. So I have to add that part of the logic in to like steer the command from one place to another.
Kind of reminds me of the way.
Carl, could you zero the IMU when you hit the cone? So it's actually just the IMU settings are only have to last until you hit the cone, and then they reset.
IMU settings.
Kind of reminds me of the way the ant moves.
No, I don't know about that one. So the trouble is that we just mixed the signals from the two places together. So there's the command from the IMU, and then there's the PID loop IMU, and then there's the command from the cone if it's present. If the cone doesn't have any command, then it's not causing a left or right. If the cone has some command, then it's trying to steer it left. But if it's trying to steer it left, and the IMU says you need to go right, well, sooner or later the IMU is going to win. PID loop.
So, Carl, would you say that the cone behavior, the IMU is always there, but the cone behavior is only there when it can see a cone? And so the cone behavior should subsume the IMU behavior.
Yes, that is quite true. And that logic isn't put in there yet. That's my point. But there's progress.
So a consequence of that could be that the cone logic runs while the IMU integrator builds up its integration correction until it can't possibly get rid of the integral term.
Well, that's very possible, because if the two are actually fighting each other, then as the cone behavior begins steering it toward the cone, the IMU behavior will see that as an error. And so it'll start cranking up the integral or whatever it is
That's my
to
point.
try to correct for that error.
That's what I think's going on. So I just have to fold in that extra logic to pause the PID loop when the cone is visible. And then after it finds the cone, I don't know if this is your question or not, Doug, but then once it finds the cone, then it it backs up approximately 90, and then it sets a new heading, which is where it came from.
That's a strategy that I'm trying to do too, because as you found out, when you back up, you get a bigger sweep too. So it's possible. Otherwise, the front of your, excuse me.
Well, mine.
The front of your robot can sweep real quick if you're backing up and turning, as opposed to trying to find it when you're heading at it.
Doug, your camera's adjusted so all we can see is your elbow.
But Doug, this one, the way this thing backs
the best part.
It says, like, if you'll watch this, what it does is, as it approaches the cone, like, it knows the heading right now as it's going into the cone. So whenever it decides that the cone is there, it triggers the backup turnaround behavior. So at that point, it says, okay, we're going to back up until the new heading is 90 degrees plus or minus 10 from when it hit the cone. So that's when you'll see at this point, it's pretty even because it's pretty much 90. It's pretty close to 90.
Yeah.
And then it comes back heading in that direction. So
yeah, what I'm saying is that when it's at the 90, if you just, okay, all right. So the IMU, where are you getting? All right, how are you? The IMU is usually in the frame of the robot, okay, and not the world. And so what I'm saying is that, so right there, stop it right there.
Oh, sorry.
Okay. All right, when you give it into 90 degrees, all right. So at this point, when you set a new heading, all right, how do you do that? That's what I'm saying. Is it because
I run this thing in absolute mode.
Okay.
In absolute mode compared to, so it's all absolute mode compared to when it was at the start. So so like what at this point right here, as soon as I hit the Robo Columbus button, it says, all right, I assume for Robo Columbus that I'm aimed more or less at the cone.
Right.
And that heading compared to magnetic north is however many degrees it is.
Right.
And that's now the reference for for indefinite run. So then at this point, it backs up 90 degrees from that. And then now it sets a new heading, which is the original heading out minus or plus 180. So the PID loop says new heading, and that's how it comes back here.
It can obviously work.
Hey, Carl, do you need that many pixels in your image? I mean, usually when I do it, I do like, you can go down to quarter VGA, and it's like 160 by 120 pixels.
Yeah, I don't.
And your frame rate goes way up, and it's kind of like TMI. You got so many pixels with a huge image. It takes a lot more time to process.
We didn't need a frame rate of. We didn't need a frame rate any higher than 50 hertz for sure.
Yeah.
But even, I mean, right now, like this is basically, what is this? This is 10 hertz. It's 10 hertz frame rate. So there's no value to going to having a higher, because we don't do frame to frame logic of any kind.
Oh, you don't?
No.
Okay.
There's no temporal part of the algorithm. It's all just frame by frame spatial. So
okay.
So there's no value, there's no advantage to go higher than 10 hertz, and there is value in having better resolution because you can see the cone from further away.
Yeah.
Carl, do you remember last 2 years now, I guess, I just used Raspberry Pi camera for something similar to this. I made a pink LED, and I was 3 or 4 meters away, and I just turned the Raspberry Pi camera resolution down to like 64 or 128, and I only read a single line. And because it was on a flat surface, I could rely on that line being available. And so I was effectively hand processing that line of pixels. And if I saw the pink LED at 3 meters, I could actually figure out which pixel it was at and target the robot.
Yeah, that's cool.
You don't even need such a fancy camera.
No, well, right. You don't need, right. But
Also, it depends on how fast the robot is going. And I think the speed you're going, 10 frames per second, is probably plenty, don't you think?
Yeah. And here's, by the way, so that was running at XGA frame size on OpenMV. I don't know what that is offhand, but whatever XGA is, that's the resolution it was running.
Isn't that 1024?
I believe you. I just don't know offhand.
Can't remember either.
Google.
I thought XGA was our upgrade from VGA back in the day.
It's 1024 by 768.
Yeah, we went from 768 by 384 to 1024 by 768.
So it's 3/4 of a megapixel, not even 5 megapixels. Anyhow. All right, well, that's my language gripe and my distract with the actual running robot for a little bit. So,
gold star.
Thank you. We're getting there. All right, and I think next we had in line we had Paul, and then Doug D, and then who would like to get on the deck after Doug D? Wow, quiet tonight.
Well, I could jump into something small after that.
John,
a bunch of slackers.
You know. All right, maybe next
Hey,
week.
no, and everybody, what is it? Hey, can I have a quick question? Or I'll talk about something small. One, those quick questions are never quick, and anybody that says I'll talk about something small generally ain't. That's just all there is to it.
Nice. All right, so
I'm
Paul,
talking about you,
what
Myron.
got? There we go. Paul is sharing a phone.
And is muted.
Like an Android phone.
Okay, if I'm trying to share my camera, I would like to use my cell phone camera.
Oh, you have it muted. Oh.
You can't use your camera while sharing your screen.
Oh. So this isn't going to work, huh?
Unless you get.
Yeah, that's working. That's working.
Are you seeing like?
No,
yes.
not your phone.
I am.
Yeah. You want to pin my phone to the?
Oh, there it is. Okay. Okay. We've got to pin your phone. So if everybody can look into their layout and find Paul's other login. I'm going to do that here on the recording computer.
Looks like part of a long robot, maybe.
Oh, Ray, everything looks like that to you.
You're right.
Okay, there we go, Paul.
Okay,
it's a very serious looking Paul.
So what?
Very serious.
What the product is a show and tell for the 2000 Robo Mower, because I've got the lid off of it, and I thought you guys might be interested to see what's in the guts of the thing.
Ray, you're right.
This is the Robo Mower, and I'll go over it in just a sec. But this is a shell, so it has a kind of like a shell that sits over the top of the thing, and underneath, I'll just flip it over.
Are we supposed to see a second view, a second camera? Because I can't find it.
All right, so you got to look at the layout to where you can see the whole like tiled view, and then if you look closely in there, you'll find Paul logged in a second time with a vertical format phone video thing.
Oh, now I see it. For some reason, okay, got it. Thank you.
Tell you what, I'll exit this login on my computer, and now am I like appearing as the primary speaker?
You are, and
Yes.
only once our echo has disappeared.
Okay. Oh, great. Great. So I'll flip it over just because I thought you might be interested in seeing what's underneath it. So that's kind of the underside. You can see there's 3 cutting blades there. It's a differential drive, so there's a caster on the front, and then 2 wheels on the back. Can you all see that?
Yeah.
Okay.
Paul, is this the robot that you entered in a Robo Columbus type contest?
The very same one. The very same one, David.
So my memory's not that bad.
It's extremely good, and so anyway, I thought you guys might be interested, since I got the lid off, in having a look at what the guts is like. So the big things here, you've got the 3 blade motors, 1, 2, 3, and 2 wheel motors that drive through a gear train to drive the wheels. And down, it's not really showing too well. Let's see if I can see this side any better. Maybe not, but there's a right in here on this little gear that you probably can't really see. There's a couple of magnets that run past a Hall effect sensor on this little circuit board, and then the yellow wires take the Hall effect output from each side of the wheel sensor off to the main circuit board. And then in this space here, this hole is where the battery lives. So there's normally going back to the case, there's normally a battery holder holding 2 lead acid batteries drops in here. So what I'm going to do is I'm converting it to LiPo, so that'll leave me a bunch of space to put electronics into the battery compartment. And then in this front section is where the hand control lives for manually driving it. Now, modern Robo Mowers drive using a cell phone, an app on a cell phone, but this is the the controller.
Always follow the safety instructions when operating the mower.
And it talks to you, and in the back of the controller is I've got a serial port plugged in, a USB serial cable. That's how I send commands to it from the computer. So I'm actually using the robot's drive electronics, and then you've got this circuit board mounted vertically. Oh, the other thing to point out is the wire sensors. So this thing here, and over here also, and on the back here and here are wire sensors for sensing the bound. So it uses a perimeter wire for sensing the boundary of your yard. And apparently they put about a 40 kilohertz signal on the boundary wire, and there's a tank circuit connected to the coil, capacitor connected to the coil, which produces a tank circuit or forms a tank circuit such that it can pick up the wire from a few inches away. It's interesting that they've got these big round things around the front pickups, but not around the back. My suspicion is that the front ones are close enough and aligned axially with the blade motors that maybe they were getting interference from the blade motors into the front pickups. So maybe they put some shielding around it, but I don't know that for a fact. And then finally, you've got the circuit board that has the power transistors that drive the motors and turn on the blade motors. And so it's the manual control has a little forwards and backwards crosshair button, and also there's a light on the thing which is on this, and I'm not going for a gold star here, just so everyone knows this is like just rudimentary, but
Oh. Oops. Did anybody else lose him?
I think whatever he did caused it to disconnect.
Yeah, I think so too.
Push the wrong button, maybe. Who knows?
What's the opposite of a gold star?
my phone just ran out of juice. Sorry about that.
Oh no!
I was going to demo sending a command to the mower to cause the motors to rotate, but another time. Anyway, that was just a show and tell for anyone who's interested in what a Robo Mower looks like on its inside.
Yeah, I was always surprised they used 3 motors, one for each blade. But
the newer ones, my neighbor's got a 2015 era one, and they only use two blade motors.
Yeah, I guess if you're Robo Mower, you can get any motor made that you'd like, So
yeah. The other interesting thing that is sort of difficult to see is the bumper assembly. And again, it's different on these older ones, but what they did with the bumpers is there's a rubber bumper with an embedded spiral coil inside of it that gets when the bumper hits something, the metal spiral coil gets pushed until it contacts a metal plate that runs across the front or back of the mower, and that forms the contact sensor for collision sensing.
Hey, Paul, Ed Mart asked what type of mower brand it is in the chat.
Robo Mower.
It's a Robo Mow, and it's the RL 500 model, which goes back to about 2000 is when this one was sold. Nowadays they're up to like RL 850 and RL 1000, and they've gone to a different kind of bumper mechanism only on the front and a solid plastic thing that gets pushed as a whole inwards. So they've stepped away from that coil contacting a metal plate inside of the rubber bumper kind of scheme. And it's all Bluetooth from a phone, so you don't have that nice USB serial port that lets you take over its mind and tell it what to do.
Paul, does that spiral spring provide some sort of shock absorption when you run into things?
No, that's provided by the springiness of the rubber that forms the bumper. The spiral spring seems to only be for the purpose of making electrical contact.
This is a problem we've talked about before, where in designing bumpers, where our main focus has always been as a sensor. But if the robot's moving very fast, it also needs to be a shock absorber. Sometimes combining those two is not simple. Doug has a real clever bumper that he's built for the front end of one of his robots that has quite a bit of movement, and it's a small robot. It uses rubber bands, but you can adjust.
I saw his presentation on that. Yeah. Anyway, that's all I had. It was just a it's always fun to look inside of stuff and see how it works. And so I thought you guys might be interested.
Well, do you have any plans for that?
Yeah, this is I'm now I've got time to work on the thing. I'm actually going to try and make it mow like in strips, like a mow auto mow, not like randomly like Roomba's mow.
Is this going to be your Ross robot?
Yes. Yes, it already is. It was when I was, when I competed it in the Robo Columbus, and so now it's like picking up the pieces where I left off and finishing them out. GPS has gotten so much. RTK GPS has gotten so much better nowadays in terms of using L1 and L2 so that you get 30-second lock times instead of 10-minute lock times. And these days with Raspberry Pis and Express IF chips, the whole, you got just so much more power than you used to just 10 years ago.
This probably has a distinction of being the most dangerous robot in the competition.
Only if you turn the blades on.
Ray will run a close second to that.
Yes,
I think Ray.
I think he's got the way more powerful and dangerous robot than this. His would run right over mine and chop it into pieces.
You should let Ray and Paul go first. That way they'll mow a path to the cone.
Service.
My memory was that Ray got actually very good GPS out there in the Netherlands where he lives. At least that was my memory, that he was able to get within a foot or so. Am I wrong about that, Ray?
The GPS RTK, I got to, I don't think it actually, I think it was GPS RTK float. It didn't go to fixed, but I didn't let the base station, resolve itself well enough or give it enough time to do that. I only did, it's like 5 minutes and 1.5 meters, which isn't enough for, that kind of accuracy. But when I was doing it, I was just using a compass and odometry. Those videos that I don't know, I think you saw them.
Yeah,
But,
yeah, they were great.
RTK.
I love that thing. That was great.
Yeah, it's kind of neat when the big junk gets, moving around the way you want it to. And
yeah.
Doesn't embarrass you, That's key.
It commands your respect.
That's right. So, yeah, I'm working on a couple different layouts of. I still want to do a all-wheel drive version versus a differential, just to kind of get the experience with it and see whether I like it better than differential drive or not. The big mower can get into situations where if one wheel is up, one of the drive wheels, it'll just sit there and spin all day, and it. So not unless I somehow sense that it's doing that, it could get stuck. So, but with four-wheel drive or skid steer, I don't think it would. So.
Back to you, Carl.
What's that? I didn't hear what you said.
I'm sorry. I thought you'd finished, Ray, and I just said
ahead.
back to you, Carl. But if you got something else to say, I'm sorry. I didn't mean to cut you off. I just thought you'd finished.
Oh, one of the things that I'd like to do, we have like 14 acres, and it costs about, I think it was like close to, I think $775 to get it all sprayed. And, basically it makes a uniform green acreage because it kills all the wildflowers. So it's pretty easy to go out and look for colors and spray the weeds because, they're all wildflowers and they all produce a colored flower. So, I could have it go out there and deal with toxic sprays and stuff like that, and kill the color.
There's some irony in that, Ray. Those flowers evolve those colors in order to attract insects to pollinate them. And
Yep,
so
yep.
you're using it instead to bring about their demise.
That's right. Yeah. So had to keep me away from the nasty chemicals and exposure and all that.
Okay, I think we had, next in line, we had, I'm sorry, I've been bouncing back and forth, so feel free to shout my name or something if I'm not attentive. But I think we had Doug D next in line, and then John G. And anyone after John that wants to put their name in already now?
Carl, you said you had to leave early this evening.
Yeah, I'll have to leave in about 40 minutes or so. I'll have to stop the recording, but you guys can keep chatting as long as you like. But I'm still trying to get ready for my early morning thing.
Well, now if a robot builder chats and there's no recording running, never mind.
That could take us another 30 minutes just to answer that question.
Does he say anything meaningful?
Just bring up PID control.
Yeah, see, that will do it right up self. Okay. So Doug Ogden, what do you got?
So I'm glad that this is kind of a night for commentary. I've put a link in the chat to. I was thinking last week, David and Mr. T were having a great conversation, in my opinion, on the relative merits to navigation via a map or via object avoidance in odometry, and I got to thinking about my plans. I've always thought that a map would be good. And I got to thinking about why, because David had a very valid point about, object avoidance and odometry is going to get you there. It may take it a little longer. And I think I'm showing my blog post here, so everybody to have to link to it. But I created this little example map, which I hope is big enough to be seen. And it kind of shows an example of what the two different types of let me see if I can make that a little bigger. What the two different types of activity would follow. The blue line would be a robot responding to the map, knowing how to get there. He gets there pretty easily. And this red line here is somebody that's doing object avoidance, and he just has to bounce around until he gets there. But he gets there. It's not too far out of line. So in my opinion, or what I decided at the end of my deal was that, oops, let me make this a little bit smaller again. I got to thinking about, okay, what's the advantages and disadvantages of each type? And I agreed with David that it was good that the object avoidance didn't take much memory, it didn't take much time to program, and it just got the job done. But the one thing that I found that the map did that the object avoidance didn't do was to be able to name a location. And I don't have a real use for that right now, but it does have the ability to give directions to the robot later. For instance, if I say, go patrol this hallway, the hallway is not a spot, it's a group of spots. And I can make that whole group of spots be hallway by giving that a name. Whereas this one couch location was a single XY spot. So even though object avoidance is going to be effective, it's sort of like a GPS in that it will get you there, but it'll take a little longer. I mean, I frequently overrule my GPS because I know there's a better way than what it's saying. But I still think that it's probably the best way unless you want to name something and take advantage of that. So anyway, I wanted to put all that down on paper just so that it was on paper and easy to review later. And I thought I would share with y'all that I had it here, and I'm anxious to have comments to see if other ideas I forgot to overlook.
Doug, can you put that link in the chat?
I did put it in the chat.
Thank you.
It's
one thing that strikes me about maps versus obstacle avoidance is that there's this sort of pathological example where, for example, you are, let's say, on the front of your house and you've got a gate entering into the yard of your house, and on either side of that gate is a fence, and you aim the robot somewhere near that gate opening and say go in, and if the robot turns left, it will go along the fence and turn in the gate and end up where you want it to be. But if the robot turns right, it will hit the fence and maybe go around the entire block or around the whole city. There's a pathological situation where the maze following might take you so far out of where you're trying to get to that you effectively, it doesn't work. And having a map does have the advantage, and here I'm the one who wants to do the obstacle avoidance over maps, but the advantage of a map is that you can say the target is a certain location, and if you are driving a certain distance away from that location following a wall, you kind of say, okay, if it's now 30 meters, I've gone way too far. Whereas if you're just doing obstacle avoidance with no map, you might have, the robot has no idea where it is and it simply just drives. So it's one of those things where in the pathological situation, which might be not uncommon, your robot just takes off and it never gets to where it's trying to get to. I thought I'd throw that in because it is one of my concerns in terms of navigating, that, turning right, turning left isn't 50-50 all the time, that depending on where your robot's running, turning right might get you there, turning left you may never get there.
Right. I kind of thought those same things in the example I gave. The object avoidance robot took off in the wrong direction and had to wander around the kitchen for a while before it got out. But it did get out. And so what's the hurry? It could be the question. As long as it's not, going to the next city to get back.
I like that answer. But if I could weigh in here, Mary, I think you're conflating two different things. And so maybe I'll conflate a third, which is that it's not necessarily an either or choice. All my robots, for example, they don't do I don't use the mapping, but you can still lay out waypoints. And so you could lay out a waypoint at the center of the gate and it'll go straight there and go through the gate. So it's not an either or. The other that I thought was being conflated was the method I've developed to switch between navigation and wall following, maze running, which I don't think is what Doug is talking about. If you're going to actually use the wall following as a maze running algorithm, which you can, you can't say, well, I'm going to go along a certain distance, and if I don't get to my goal, I'm going to turn around and go the other way. You'll never get out of the maze. You can't say sometimes I'm going to follow a left-hand rule and sometimes I'm going to follow a right-hand rule. You have to pick one and stick with it. If you're really in a maze, if you switch back and forth between it, you won't get out of the maze. So I tend, though, to fall down along what Doug is saying, which is that I'm more entertained by watching the robot find its own path than by me giving it a path. And me being entertained by my robots is the whole goal.
Maybe I can think of an example of your robots, and it's the one where you aim the robot at a field on the other side of a building, and it goes in and does that little cul-de-sac in the front of the building, and then finds its way out of the cul-de-sac and around the building, and finds its waypoint in the field, 1,000 meters away. And the only thing that I could say is that your robot, when it hit that cul-de-sac, it did a wall following. I think it went left and then followed around. But if it had gone right, it would have gone the other way around the building. And if, let's say, the other way around the building had a fence that went off into infinity, the robot never would have got to the field.
Well, I will definitely agree that my robots will not work with fences that go off to infinity. I'll give you that. In that particular case, I know Pat had said something about it turned right, and if it had gone left, it would have had a shorter route. But that's not actually true. That little cul-de-sac was right in the middle of the building. So whichever way it chose, it has to stick with that. If it had gone to the right instead of to the left, it would have still had to go around half of a building to the right rather than half of a building to the left. Now, your example was the Great Wall of China. And I freely admit that my robot is not well designed to handle the Great Wall of China. Everybody here whose robot is well designed for that, put up your hand. I understand we've talked about subsumption before as a control paradigm, which is what it is. In my mind, subsumption is like PID. It's not artificial intelligence. It's a mechanism for setting up, but there's more to it than that. Subsumption, this is a longer discussion than we can go into tonight. But
it's interesting because I was trying to get you to start on that discussion.
Well, I will summarize it this way. The common practice in building robotics, as described by the behavior trees that we went into a few weeks ago, is a deterministic method. That is, the robot solves its problems the same way that we envision that we do. Subsumption is not a deterministic method. It's a chaotic method. And as a matter of fact, if you build a subsumption robot and watch it run around, you can see all of the classic characteristics of chaos theory. You see strange attractors, you see it fall from one strange attractor to another. So it's a different way of thinking about the robot. You have to release control. Deterministic is saying, I want the robot to do what I would do if I was driving it. You have to release that level of control for subsumption. And as Doug says, it still gets there, but you don't get to tell it how to get there. And I will add to that if you build a balancing robot, because the balancing robot also has to balance, you can't arbitrarily tell it where to go. It has to make its own decisions about how to get there. So you have to release even more control. And that's all I have to say about that.
But David, did you not use a geofence?
Exactly what I wanted. Oh, go ahead, Pat.
Did you not use a geofence in one of your robots?
Yes.
On your videos?
Yes.
And that was to keep it from going off to oblivion.
Yes. Yeah, actually, that's a real valuable thing to keep it from like going into a swimming pool or driving through somebody's expensive garden. You just put a geofence around it.
So that's a kind of a map. It's a piece of a map.
Well, that's why I'm saying they're not exclusive. It's not just mapping versus, react.
But I think where they differ most fundamentally is in the planning phase. So there is no planning phase in subsumption, whereas in the diagram that Doug showed, there was a planning phase where it planned the route out. And so you earlier cited as an example, I think, of using a map, that you could put a waypoint in the middle of a gate and it would head towards the gate. But that's not planning using a map. And that's the big difference, I think, that is.
Well, and it's at least the way I do subsumption. I allow the robot to have predetermined waypoint lists. And that's not a map of the environment, but it's definitely a map of where you want the robot to go. And if there are objects in between, then it automatically on its own will avoid those objects on the way to the waypoint.
It's not a map, it's a path.
Yes.
A map is a diagram or a representation of the world through which planning can be done.
Yes.
A path is a sequence of movements that should be taken.
Well, it's not really a sequence of movements, it's a sequence of goals.
Sure, a sequence of relative points that should be achieved. But that's different than an a priori map of the environment.
Agreed. And one of the problems, Doug, you might want to look at this. One of the problems with doing one of the chief problems with doing mapping is trying to keep the map updated and correct for the position of the robot. Because we as humans do that so trivially, we assume that it's a trivial task, but it's not. So even if I gave you a map, you don't have to make it. I gave you a map. Nonetheless, keeping track of where you are in that map and keeping your internal representation of the external world up to date is not a trivial task.
Yeah, and Doug points out that the use of the map takes programming space, and that's true in spades for exactly the reasons you're bringing up. However, I'll raise a point here in favor of maps that if you're doing a commercial product, it's laughable for someone to see their mining truck, for example, take a loop around the parking lot before it goes off to the mining face. So there's a certain level of professional intent that I think demands the use of a map in a lot of professional contexts, unless what you're trying to do is just cover the space, which is what lawn mowing robots do. It doesn't matter where they go, they just have to cover the space.
I think I would, I don't disagree with that, but I would add to that all of this presupposes that you're running your robots in known environments. I spend a lot of time, especially with my outdoor robot, just stopping at an interesting place alongside the road and setting it down and letting it run. I don't know the space. I don't know the environment. So if your robot depends on a map, that greatly limits what you can do, and you certainly have a much harder time just setting it down in an unknown environment.
That's true. And
yeah, I don't disagree with what you're saying, but it has very limited usefulness in that you have to know the environment that you're running in, and probably for most cases that's true, but for me it's not.
Yeah, you make a good point, David, and I agree with that. But then going back to the commercial applications of robots, they always have a goal. There's always some goal there, and the goal drives what they need to do. And a lot of times the goal sets the context, and maps are inappropriate. Oftentimes there is a context that they know, where they do know where they are. Even for self-driving cars, they know where they are.
Or we're talking about the generalization of requirements drive design. Okay, come on. we most of us here are pretty much well steeped in that in our careers.
Yeah, and it's wonderful, and I applaud that you enjoy seeing your robots drive, and that's sufficient pleasure for you, and your robots certainly drive among the best that I've ever seen, and but that doesn't make them a commercially viable robot, and that's the only point that I'm making, is that if you want something that really you can sell for something,
and the point is that's not his requirement.
Right. Yes.
Now wait a minute. You're saying that the kind of robots I build are only useful if they have no use?
Have you guys seen you guys seen the world's most useless machine? The one that, like, when you flip it on, it reaches out of the bucket and turns itself off again?
And Paul, that's a commercial product. It is.
You can buy them right now. In fact, they've got some where it's just not got one button. They got like some that are built like 10 or 12 of them long, so you can turn that one off and that one off and that one off, or roll them off, and they turn them all off. Yeah.
Kind of reverse whack-a-mole.
Exactly. Pretty funny.
Hey, David, you claimed subsumption was non-deterministic. Do you want to take that one back, or do we want to have a go at that one?
Subsumption is the new kid.
As I pointed out, that doesn't cover what I do.
Say that what doesn't cover? Subsumption doesn't cover what you do?
Non-deterministic doesn't cover what I do, because I can put in paths and waypoints and so forth. I can have goals. It's not just wandering around randomly. I'll tell you a better term than non-deterministic: stochastic.
Okay.
And I could give two simple examples. You want to paint a canvas white, and so you get a brush and you apply white paint to the canvas, and you have to do that carefully in order to get it evenly distributed so that it's a smooth white. That's a deterministic process. On the other hand, you could approach it with a stochastic process, which is we could spray paint it. In the stochastic process, we're going to end up with millions of little tiny specks of paint, and we actually don't care where any one of them in particular goes. We're looking for the final finished effect. We're looking to get to the kitchen, whatever path it takes. So the painting of that canvas with a brush is a deterministic process. The spray painting of it is a stochastic process, a process that involves numbers that are so large that we effectively can treat them as random. And it's really not so obvious unless you sit down with a subsumption robot and watch it behave. Over a period of time, you'll notice that it's doing the same behaviors over and over again. And but that has to be a long period of time, hours. And you'll also notice that there are, as I said, there are strange attractors. So it'll loop around in one particular environment for quite a while, and then it'll fall out of that attractor and into another, and it'll loop around in another environment. The talk I gave 10 or 12 years ago, I began with a algorithm, which some of you may know, Z equals Z squared plus C, where Z is a complex number. That's the Mandelbrot equation. And so from that little tiny equation, Z equals Z squared plus C, you get all this incredible, deep complexity. And I believe that the way I approach robots is the same, that rather than going at it from a high level with a very complex deterministic algorithm, you go at it from the low level, from the lowest level, with a Z equals Z squared plus C that produces that high level complexity.
Still a deterministic process, though.
You think the Mandelbrot set is a deterministic process?
The math is deterministic.
It's
the
the
results
root
of it are chaotic. They're not incompatible notions, I don't think. Are they?
I think chaos theory is very different, very different. If you look at linear physics, look at a sine wave. If you zoom in on that sine wave, the closer and closer you get it, the more and more it approximates a straight line. Till eventually, if you zoom in far enough, it is a straight line. If you zoom in on a Mandelbrot set, the more you zoom in, the more complex it becomes. It never resolves.
It never resolves. I get that, but it's still a deterministic process to get there. The math is deterministic.
I'll have to think about that.
Okay. Paul, I have a question before it gets too far away here. In the case you were saying that, well, for commercial product, you were saying, you mentioned that how would I get out of a parking lot? So now, in your commercial product, is the parking lot mapped? Is it waypointed? How does the commercial robot get out of the parking lot?
It was mapped, and
well, okay, so it's mapped. So he has a map of the parking lot.
It has a map of the parking lot and the road that led out of the parking lot.
Yeah, but not all the way to Baltimore, I hope. You know what I'm trying to say?
No, but
to
the destination the application required it to go to.
Okay. Yeah, but what I'm saying, you know, the actual robot, even though he may have a map or a region, when he starts moving, if there's cars parked in the parking lot, he's building the map as he goes along. And really, you know, depending on how many cars are in the robot or in the parking lot, his map really isn't seeing very far. You know, he only knows, well, let's say in front and to the side, what he's mapping. And it's only to the distance that he sees an object, and the map itself is really just a big square or rectangle. Okay, so you know, the map that's actually effective in the robot is only what its sensor sees at the moment it makes its particular movement. So like if it goes from T1 to T2, you know, it moves so distance, then the map changes, it makes another path. Now, what it's using some algorithm like A-star or something to find the best path out of what it knows. But it only knows a little bit. So it's constantly changing that path, and that's why, you know.
Well, no, I don't think that's really true, Doug. It
Okay.
has a global path, and Chris showed us that.
But when you say a global path,
So
or is it a preferred path?
It planned a global path at the beginning without knowledge of these obstacles that are yet to be discovered, um, and so it's a path that would be optimal if there were no obstacles. And you correctly state that it does discover more about items, objects in the map as it goes, and has to replan, but it will, or it should, try to drive towards the global path, because that was computed and is thought to be in some way optimal.
Well, that's what I've been looking at. It tends that you actually create the optimal path as you know more. Okay, now if you were just saying, let's say in this case he wants to go to the living room. All right, we could assume the map would know where the walls are.
Yeah.
All right, so you could put that in the map. And you might say he knows where some of the furniture, but I'm starting to think that would probably,
right,
unless it's something that isn't
probably
part
not.
of the wall.
Probably not.
Yeah.
Yeah.
And so he's moving along. From his goal to where his location is, he creates an optimal wavefront type map or some form of map to say this is the optimal path to go. Right.
Right.
But I don't think he retains that path, does it? It really.
No, he does retain it, and he tries to re-achieve the path through that pre-planned global map, while dodging obstacles. And you see that in the blue line where he dodges the furniture, right about where your cursor is.
Yeah. I don't see the cursor. Oh, okay.
Yeah, right there. So yes, he could use A star or other planning algorithms in both the global and the local planning phases. But the point is that the global plan is thought to be in some ways optimal. At least you hope it is. It should have been designed to be that way. And
but
then,
isn't that just a set of waypoints?
Yes.
Okay. So
but the point is that the waypoints were derived from a map of the environment, emotion. So it was a pre-planned route, which is what makes it fundamentally different than the bouncing off of obstacles.
Okay, so it sounds like as if he took everything out of the kitchen, hallway, and living room, except the walls, and you did a whatever algorithm, A star, whatever you wanted to do, it would plan a plan. It would give you an optimal plan. And you're saying you retain that first optical plan.
Yep.
And then everything is really an adjustment to that plan.
Yep.
So you don't really calculate paths anymore. You're just trying to go to the mapping grid point that is on the plan.
You still have to, well, it depends on the implementation. So like maybe you could use subsumption to get around an obstacle, but your end point, your end goal should be to seek back to the global plan, because if there are no more obstacles, like say there are only obstacles in the kitchen, but none in the hallway and living room, then you would run the optimal route, because once you'd dodged the ones in the kitchen and seeked back to the path.
But what I'm trying to get at is, okay, so once I assumed an optical path, that if I look at it as a grid overlaid on top of this house plan, all right, there are each grid location, the block inside of the grid, would be part of the original path. All right. So now, if I don't have to recalculate the path anymore, that's a big savings in if I don't have to every time I move calculate the best path. If all I have to know is I have to go to one of these squares. Now the question happens is okay, so you're moving along the path and you see an obstacle, you have to go around, it's off the path, but then it tries to get on the path. So it's like literally a grid of waypoints. That's the original path. Yep. So if something sits on the path and makes a grid unavailable, then it has to go around it. So it would then reassume, okay, from this position, the closest way to the path is to the block behind it or whatever. Okay, I think I'm following, but this, if you didn't have to create the optimal path back, that's a big step.
So
now the other,
when I was doing this, I haven't actually implemented it yet, but my intention of how to implement it is that as you were saying, you make the original at the beginning, you say, here's my best path, not knowing about maybe something's changed. Because like you also said, the wall is pretty immutable, but the furniture and all that can be moved. There could be a dog here or whatever. But you're following the best path using object avoidance until you get to an object. At that point, you have to avoid the object. And then, as you were saying, almost what I was thinking is at that point, you recompute a new best path. Anytime you have to deviate from the original best path, you now have to recompute a new best path.
But that's not what Chris showed us. What Chris showed us was, the optimal path, which might pass through objects, and that when you had to deviate from that path, you didn't then calculate a new trajectory to the waypoint. You got back on the original path.
Yeah, see, that's where I'm not quite intending to implement the same way. It happens that this path goes back to this waypoint, but that's because from here, that's now the new best path, not because it wants to get to that waypoint.
If you remember a few weeks ago, I did some simple demos of the robot driving in a straight line back and forth, and then I put a cardboard box in the way.
Right.
So when the robot avoids the cardboard box, it does not get back on that straight line.
Right.
It calculates the shortest path to the
from its new location.
And what Paul is describing is that you actually have to get back on the original path.
And just to clarify, Doug, I described you seek towards the original path, but I don't think there's anything that requires you to seek to the original path versus creating a new global path from wherever you end up after avoiding the obstacle. I don't know of anything that restricts you in that choice.
No,
that's what Doug was complaining about, I think.
Well, no, what I was just trying to say is the approach I was playing around with, every time I make a step, I reassess all my sensors and I create a path. Now, the problem is that I really want to see and where I want to make the step is, okay, I'm in the kitchen and say I want to escape the kitchen, but I don't want to have the whole house, gridded. I wanted just to have the kitchen gridded. And as I move forward, I want my grid to shift with me. Okay. Because otherwise I don't see why a map would be made to do this project. Otherwise I would have 1, 2, 3, 4, 5 waypoints and just let it go.
Well, imagine a mining truck driving from a dump to a mine face. There are roads that it has to traverse, possibly multiple roads, and
I understand that, but what I'm trying to say is, in the case like that, the robot, I mean, the car, in that case, the car would be trying to identify that it's on a road. And, you know, it's not just driving to a place.
No, you can think of the road as being on the map and having boundaries that
Yeah.
it should stay within.
Yeah.
And so,
I'm sorry, Paul, go ahead.
No, go ahead, David.
Just backing up and kind of throw your eyes out of focus and look at this problem from the larger perspective. You know, we were talking about a month or two ago about how none of our robots are anywhere near as intelligent as a honeybee. So let's take a honeybee, and this is our commercial application. We've got a semi truck loaded with honeybees, and we're going to drive that. We've been hired. We drive that to a farm's field, and those honeybees have never seen that field before, and they have no map. And what they do is they fly out and they try to find sources of nectar. And when they find those sources, they turn them out and they try to fly in as straight a line back to the hive as they can. So they know where the hive is, right? Even though they have no map, they know how to get back to the hive. Secondly, as they fly back, they're memorizing both the angle and the distance. They're collecting that information. So in that sense, they're doing some very primitive map making, right? And then when they get back, and remember, they're flying around obstacles and so forth on the way. That part's being handled by the hardware, right? But when they get back to the hive, then they transfer that map to other members of the hive by doing their little dance. They say the honey is at this angle to the sun and this far away. And then the other, I think I mentioned, they actually have a sample of the nectar with them. So the other bees can make an evaluation as to whether or not that's worth the trip. That's an awful long way for this mediocre nectar you came back with. There's also another dance where if the nectar is just somewhere close to the hive, they don't bother with the angle and distance. They just dance in a circle. The message being, just go out and fly around the hive, you'll find it. So these are instructions rather than maps, right? Now, again, I don't think that we do it the way that we're describing here as deterministic. I don't think that's how we do it. When I used to ski a lot, you start off at the top of the hill where there's a lot of moguls. You have a general idea of which way you're going to go, but you're correcting that all the time. You will not be able to predict the actual path that you take down in advance, because every time you hit and jump, it changes it a little bit. So you're constantly building a new map. So I do not believe that we navigate the way is being described here. And I don't think honeybees do either. And I just add on that bees do it better than our robots do it. So maybe that's something to look at.
Hey, Paul, when you do your talk on the 11th, you know, what's the word?
Presenter.
As a presenter, I guess, so that's why not. Can you kind of like describe the process of starting it up, going out of the parking lot, getting on a road, going to someplace, what it knows ahead of time, what it, you know, how it determines the boundaries of the road and whatnot. I mean, I'd be real, you know, I don't know. I don't want to tell you what to say, but I'm just,
that's going to be too big a topic and too specialized to take on in a broad talk. But,
all right.
but I can address strips. But I can address that here. I mean, the map was expressed as a series of vectors, which encompassed a parking lot and connected roads, and connected mine face, and so it would plan a global plan. And sometimes the global plan was good, and sometimes it was not good, and very suboptimal. One time I told it to drive about 20 meters straight ahead to a point straight ahead of me, and it chose to drive right around the edge of the parking lot before it came back to the point I directed it to. And so I guess the more advanced point about path planning that I wanted to bring up is that it's actually a pretty difficult problem, and A star is a nice algorithm that works in gridded areas.
Yeah.
But when you're dealing with, but there are other approaches, and one of them that's frequently used, especially with ARMS, is called random. Oh no, what's it called? Random route traversal (RRT), and and it is exactly what it suggests.
Say that again, Paul. Random what?
Random route traversal, RRT, and it's a part that family of algorithms is a part of a package called Oompa. I forget the name of the package, but
Oompa Loompa?
the point is that it's actually a very non-trivial, a very difficult problem to construct paths for a 7-DOF arm to move all the right joints in the right ways in an optimal way, so as to cause the end effector to move from point A to point B. They're especially for an what's it called? Under constrained arm, I think is the name. When there's 7 joints, then there are an infinite number of possible paths where from the end effector being at one point to another. And so what companies do is they use this random route traversal, but it truly is random. And so on one of the robots that had an arm, it would sometimes it would go like that to reach this pose, and other times it would go like that to reach the same pose. And that was the example I gave, where it drove around the parking lot to achieve a point 20 meters in front of it, was an example of what can happen with this random route traversal. And I talked to the guy who was doing the algorithm, and he said, yeah, that's what random route traversal does. And you try and prune it, so they will try various measures, like it might circle the kitchen 3 times and then go out into the hallway and then do a back and forth and then down into the living room. And so they'll pick various points and say, can I produce a more direct path? But you end up with a somewhat random approach that is not optimal in the way that A star seeks to produce an optimal global route.
Yeah.
Nevertheless, I stand by the assertion that a global path should be created that is hopefully in some way optimal, whereas a bounce off the obstacles is not trying to be optimal.
Oh, yeah.
I resist calling the approach bounce off the obstacles. Let's call it intelligent interaction with the environment.
Yeah.
We'll call it David's approach.
Okay, so I want to go to downtown Dallas, and I have a rough idea, but I don't have a global plan. And okay, here's a one-way street that looks like it's going in the right direction. I'll take it. And, in this way, I find my way to downtown, but I don't start with a global plan. I only start with the destination in mind. And I create the plan as I go. Oh, I'd like to turn here, but no, there's a car in the way. I'll go to the next block. Oh, no, it's one way. I'll go to the next block. Yeah, this one will work. So I don't think that's the way we do it at all. And as I say, I don't think it's the way the honeybees do it either. So
I agree.
Or the honeybees a model.
Right. I agree with that, David. And you described the honeybees as using a map, and I disagree with that. I don't think
I didn't say. I said it was like mapping. The fact that they know where their hive is and that they can determine the distance and angle.
But it's not like mapping, because mapping involves a map which has a global representation of the environment, including boundaries. They don't have that. They have more like these paths.
But the paths are a set of vectors, right? And you
They
said
don't need boundaries.
And you said that your map was a set of vectors. For example, your map probably doesn't include the boundary of the Atlantic Ocean.
Yeah,
It
yeah, but
probably-
I think, David, that you're doing what Paul said, living in a desert with the beast.
Not at all. Not at all.
I mean, there's, you know.
And when we talked about this before, my suggestion was that a robot following a hallway was no different than a truck following a road. It's in a constrained environment. It's not out in the desert where it can just go anywhere it wants to
Agree.
get.
Yeah. Well,
But also, as I was demonstrating here, with my multiple degree of freedom hand, I can actually approach this from a lot of different ways. And I don't know that any one of them is more optimal than the other. I guess it would depend on what your task is.
True, but oftentimes a task has a defined start and end pose. So for an end effector on a robot, there typically is a defined start and end pose, like where the component is it's about to pick up and put on a circuit board, or where the dump face is and the dump that it's supposed to take a load to and supposed to back in. So the pose at either end is oftentimes defined.
I think you guys have
put this on my nose.
have kind of devolved into semantics here. I mean, because let's face it, if you remember anything about where you've been, you have a map. It's an imperfect map, but it's the beginning of a map. If you remember anything, it's a map. It's elements of a map, but it's not perfect. Right?
Okay, this may seem off topic, but to me, it seems totally aligned. I had a senior level course at university called Comprehensive Musicianship, which was a pretty interesting class. And one of the first exercises they gave is 30 people in the class. They're all, musicians. The professor asked us to come up with a definition of music that we could all agree on. And it's a trick question because you can't get 3 people to agree, much less 30. And so everybody's going around the room. And he said, I want everybody to tell me what is your favorite music and your least favorite music and tell me why. So there's these 2 guys sitting next to each other. And one of them says, well, my favorite music is Bach because of the mathematical precision and timelessness of it. And my least favorite music is jazz because it's just guys up there screwing around. And the guy sitting next to him says, well, my favorite music is jazz because it's the individual expression of a person that's only true for that moment in time and changes from one moment to the next. So if you hear the same piece the next day, it's different. And my least favorite music is Bach because, maybe this player hit this one note harder than this note, but it's pretty much always the same every time you hear it. So I'm expecting these 2 guys to look at each other and say, what an epiphanous moment. There's not one right definition for all of us, but instead they look at each other and say, jerk. Have we already lost Carl?
I'm still here, but I'm about to bug out pretty soon.
Well, Carl, should we all just call it quits tonight? I think I gave the perfect antidote for our ending.
Yeah, I really like that. I was listening in, and that's pretty phenomenal. I'm good to end it if you guys are. If you'd like to keep chatting, I think I said John G and Doug P still on queue.
Oh, I'm sorry. Well, Paul, I greatly look forward to your talk, and I bet the Tuesday after that we'll have lots of things to ask about. So thank you so much for doing this.
I just had brief status on our collaborative motor driver project. If you're ready.
So I'd say John and Doug P, why don't you guys dive right in, and I may or may not sign us out, but just continue on.
I'll be brief. We got our boards delivered by PCB Way. So now we're ready to start building them out. And I realized I was going to try to have something built today, but then I realized I am short a couple of parts. That I had the wrong footprint for the parts, but I'm putting everything else together, and just to show off my anal retentiveness, I've put together a box of just the parts that I need because I don't want to be fiddling with pulling parts off of the cut tape while I'm trying to put them on the board, trying to minimize the chance of error as much as possible.
I am so impressed.
especially because capacitors unmarked. And if you drop one of these boogers, there's no way to tell what value it is. So, so I've got my stencil, just getting everything ready for when the parts come in on Thursday. So I got my stencil taped to the board.
Oh, wow.
Positioned.
And
So you actually
John,
need a
just for
soldering.
just for everyone's edification, could you tell us the spec of the board? Is it 5 amps per channel or what?
Yeah, five amps per channel, and I'm having trouble. I'm having trouble believing that right now because let me bring this picture up that I just posted on Discord. Let me do a share here.
I think it's a 4 millimeter square.
Less. And let's see, screen.
A very hot
There.
4 millimeter square, right?
Yeah.
All right, so where's Discord? I can't find Discord. There it is. Can you see that? Can you see Discord?
Yep.
Let me go ahead and open this picture. There's the part. There's the driver on the penny. That supposedly can handle 5 amps. And I'm having a real hard time believing that spec.
Yeah, but you can get some very low RDS on MOSFETs these days. I mean, you know.
Yeah, it's only 65 milliamps per channel.
John, I think the question you want to ask, I think, is not amps, but watts. How many watts is that thing supposed to dissipate when it's pulling 5 amps?
I mean, there's the pad, which is only 0.2 millimeters wide and 1.3 millimeters long. And I've tried to make the traces on the PCB board as wide as possible without violating the design rules that PCB way requires. But man, I guess there's only one way, as Shurik, one of our participants pointed out, there's only one way to find out. You know, put it together, smoke test it. So hopefully when I get my parts in on Thursday, I'll take a stab at putting that together and popping it in the toaster. And I've already got some test code written. So maybe I'll have something to get a gold star for next Tuesday.
And you got your toaster oven, your automatic toaster oven all set up and working?
Oh yeah, I tested it out. My Adafruit do-it-yourself reflow soldering oven is all ready to go, and did a test run on it. Works fine. Doesn't set the house on fire. And just one last thing. Somebody mentioned Mandelbrot. Oh boy.
There you go.
Years ago, I wrote this Mandelbrot program in Java, so you can go around the Mandelbrot set and explore different little pieces of it and dig down further and further and find these interesting little patterns and play with the colors. So anyway, I'm a big fan of Mandelbrot.
Very, very cool, John. I did the same thing.
You what?
I did the same thing.
You did?
Actually, I had a project for JPL many years ago where we had to come up with an interpolator for radar data, and I ended up using a chaotic interpolator to great applause. Those pictures ended up being published in National Geographic. The only pictures I've ever had that were published as a fold out in National Geographic.
When you say pictures, you mean pictures of your graphical data set?
We had side scan radar reflections off the surface of Venus, and we also had altimetry data. But the side scan radar had a resolution of about 1 meter, and the altimetry had a resolution of about 1 kilometer. So what they wanted to do was basically interpolate the altimetry up to the level of the radar, and we did that with a fractal interpolator, which looks a whole lot like landscape. I mean, it looks like rocks.
I should post those pictures sometime.
Look at the December, Look at some December issue of National Geographic.
All right, next up, I'm
50
done.
years of National Geographic right now.
Who else did we have here?
Doug Parody.
No, that's fine. I can let somebody else take it. I just had a small thing.
I think you were it.
Doug, you're it.
Oh, well, okay. I just wanted to, everybody has been building robots for any time. It eventually runs into Parallax, the company. And they have a Bobot robot that is a lot of fun. It's a lot of fun to play around with. But anyway, there was one of the problems that on a lot of my robots that I've had to try to deal with is that the space in the front of the robot is very valuable. That's where all your sensors are. And if you're trying to throw in a claw, you're trying to throw in a bumper, but that space in the front is very valuable. And the guys at Parallax know this too, and they came up with an interesting variation on their claw. And if you'll just let me present here for just a second.
It's a bumper claw. Yeah.
Well, no, I'm just saying that this is their attempt to try to give themselves more space on the front of the robot. Let's see if I can find it. And I just thought it was an interesting idea. And that's, okay. So here's their claw. But do you notice they have a little rod here? Okay. What they're doing is instead of using all of that real estate that's right here for their servo, they're actually mounting their servo in the back with a rod. And I really thought I'm not sure exactly how, practical it is, but it definitely is an interesting idea and out of the box for what I was thinking, than my thinking, not necessarily everybody's, but I just wanted to say, kind of cool. All right, that's it.
Yeah, mechanical advantage, it doesn't look to be that great though.
Yeah, I don't know the details. I know it costs a lot.
Well, yeah, I was looking at the diameter of the gears at the base of each segment of the claw. They weren't that great in diameter, so the mechanical advantage must not be terrific. Probably can't grip very hard.
I don't know. You just have to.
Depending on what you're gripping, I'd throw in the only gripper I've built was the one on the SR04, and what I did on that one was I mounted the gripper directly to the bumper, because that way, if there's something in the gripper and you bump into something, it automatically inherits all the behaviors of the bumper. And that one, each is driven by a little tiny servo that are actually mounted underneath the front edge of the bumper.
Yeah.
But I'm totally with Doug. That front end real estate is valuable.
Yeah.
Well, it's kind of like the design. If you've seen the designs of robotic hands that people create, space is a premium, and it seems like the only way to get any appreciable amount of force out to the fingertips is to use something akin to tendons in a hand.
Well, look at how we do it. None of those muscles are in my hand. They're all down here, right? They're long, powerful muscles down here so that the hand can be lightweight and play the piccolo.
Okay. Well, it looks like we've lost, I don't know, have we stopped recording?
We are still recording, but
okay. Well, I say I'm with Dave. Let's call it quits for tonight.
All right, guys.
Turn it off.
Good night, all.
Good night, guys. Good night, guys.
Catch you next week.
See you next time.